myself that you ever make you cry. There's nothing left to say but goodbye.
Internacional. Obrigado.
Good morning, everyone. Oh, good morning, everyone. Today we're going to assess you if really did you study the English or not. Okay. As we know that this activity is international activity, we're going to be using English. Those people who they are not able to speak in English, they can use another language, and then we're going to translate to English. Thank you very much for the organizer, and thank you for the opportunity to choose me as a moderator. I would like to invite our president, the president of INSTA-QT. When he's coming, we can applaud, we can put our hand together to welcome our president. Let us go.
Minhas senhoras, meus senhores, mais uma vez, bom dia. Saudação especial para os nossos convidados, particularmente ao nosso querido amigo aqui de casa e diretor do projeto espacial, do programa espacial. Este programa espacial, devo dizer-vos que é algo que me fascina. Entre as coisas que me fascinam está o espaço. E este programa espacial explora o espaço. Eu gosto do espaço porque é infinito. E é na infinidade que mora o certo e também o errado. Dizem que Deus mora no espaço, porque Ele é o próprio espaço. Então, esta é uma das razões pelas quais, quando eu fui mais jovem, quis estudar astronomia. Portanto, alguém que conhecesse dos segredos do espaço. Os astros me fascinam. E a atividade do Dr. Zolana está virada para esta área do saber. Portanto, Dr. Zolana, por gentileza, arranja um programa para nós, convida o ISPTEC, nós e os estudantes teríamos muito prazer de visitá-lo na sua área do saber e do fazer. Caríssimos, é consabido que o maior flagelo da humanidade em nossos dias nem tanto são as endemias, nem tanto são as pandemias. Sem dúvidas, o maior flagelo do nosso tempo, no nosso tempo, é a fome. A fome, este mal, atinge a humanidade. E atinge a humanidade por via da seca. Só verdadeiramente há fome quando há seca. Porque a Mãe Terra, a Mãe Natureza, esta sabe providenciar os víveres para os seus filhos. Mas quando há seca, até a natureza geme. E a seca é precisamente a ausência das chuvas. Não há água. E isto favorece os desertos. E os desertos expandem-se em detrimento dos espaços agrícolas, das terras aráveis, das planícies, que por sua vez o seu recuo, a sua retração ameaça de morte a agricultura, que é considerada das maiores, ou das atividades mais antigas da humanidade. E segundo registros, a agricultura remonta aos tempos da Mesopotâmia. É lá onde ela nasce e por via do difusionismo antropológico, a agricultura expande-se por todo o planeta. Mas ela é originária precisamente da Mesopotâmia e numa altura em que certamente a Mesopotâmia e o Egito tinham ligação. Feito este introito de abertura, queria então saudar todos os participantes à escala nacional e internacional a este importante evento que trata da água, que trata da agricultura, que trata das tecnologias quânticas enquanto meio para a solução deste flagelo, que é a seca. E então, dou as boas-vindas com imensa satisfação a todos que participam deste workshop internacional INSTA-QT, Tecnologia Quântica sobre a água para a agricultura, com um foco especial para o Objetivo do Desenvolvimento Sustentável, Fome Zero. Como presidente do SDG, tenho a honra de sediar este evento de pesquisadores e especialistas determinados a buscar soluções inovadoras através das tecnologias quânticas aplicadas à agricultura. Minhas senhoras e meus senhores, a temática do presente workshop, com o tema aplicação das tecnologias quânticas para combater a fome global, destaca o impacto profundo que os avanços em sensoriamento quântico e tecnologias relacionadas podem ter na conquista do objetivo, que é o desenvolvimento sustentável das Nações Unidas, Fome Zero. E este objetivo não é apenas uma aspiração, mas um compromisso com a segurança alimentar e a promoção da agricultura sustentável à escala global. A importância da água na agricultura não pode ser minimizada. É um recurso fundamental que sustenta a vida e desempenha um papel preponderante e crucial na produção de cultivos. Com as mudanças climáticas apresentando desafios sem precedentes, encontrar maneiras inovadoras de otimizar o uso da água para a agricultura torna-se imperativo. E as tecnologias quânticas oferecem uma promissora via para revolucionar e impactar a relação água-agricultura. Ao alavancar as capacidades do sensoriamento quântico, visamos aprimorar a compreensão da dinâmica das bacias hidrográficas, as condições do solo e as variações climáticas. O presente workshop fornece então uma plataforma única para especialistas de campos diversos colaborarem, compartilharem e contribuírem para o desenvolvimento de soluções inovadoras. A energia entre tecnologias quânticas, repito, a sinergia entre tecnologias quânticas e o contributo pela Fome Zero está alinhada com o nosso compromisso de promover conhecimento ao serviço da humanidade. Hoje, e neste workshop, aprofundaremos discussões e demonstrações que ilustrem o potencial das tecnologias quânticas para enfrentar os desafios da escassez da água, das secas e das inundações na agricultura. Só assim podemos pavimentar o caminho para um futuro em que a ciência de ponta contribua significativamente para a prática agrícola sustentável, garantindo a segurança alimentar para as comunidades ao redor do mundo. Exorto, por consequência, todos os participantes a participarem ativamente das sessões e trocarem ideias e estabelecerem colaborações que transcendam fronteiras. O conhecimento coletivo é a chave para um mundo sem fome. Mais uma vez, são todos bem-vindos ao presente workshop internacional sobre a água para a agricultura. Que os nossos esforços conjuntos contribuam para um futuro em que a tecnologia e a sustentabilidade e a compaixão se entrelacem para superar desafios globais. Declaro, por conseguinte, aberto este evento sobre tecnologias quânticas, água e agricultura. Muito obrigado.
Wow. Thank you very much, Mr. President of INSTA-QT, for great introduction. When President was giving his speech, we could see the anthropology inside. And even there are things that you forgot, but today it came back. Continuing to our activity, as is declared that we are starting now, I have the honor to invite the first speaker, who is Dr. Zolana. But before him to come, let me give you a brief statement about Dr. Zolana João. Dr. Zolana João served as the first general manager of Angolan National Space Officer, where is driving engineering and research challenge on communication and Earth observation satellite launched with patent agency and government worldwide. He was instrumental in designing the current Angolan space strategy, in additionally to launch ANGOSITE 2 into orbital to provide broadband communication services in Africa and to minimize the digital divide on the continent. He also leveraged Earth observing satellite to detect whale and speed in the ocean and predict agriculture crop, to using a space to support progress toward of SDG. He holds a doctoral engineering degree from George Washington University in US, and also is specializing in managing large-scale and complex projects. Dr. Zolana also is a supervisor of MC students, and we hope that he's supervising some PhD students from France and also in the US. He's doing great work. He's one of the Angolan who is making Angola to be proud internationally. Please, let's put our hand to welcome Professor Dr. Zolana, please. Our speech is in English. I think you guys, you are watching us or listening. If you have anything that you are not understanding properly, let us know. We're gonna help with communication.
Não tenho o visual da apresentação de frente, então vou ter que ir olhando a tela. Eu queria primeiro agradecer o nosso presidente, João Fernando, por permitir eu estar aqui, a seu convite, Dr. Marcílio e toda a equipa organizadora. Obrigado por essa iniciativa. Queria saudar também todos os docentes dessa casa. Eu acredito que os docentes são os alicerces de qualquer país. Eu penso que é um trabalho muito nobre que o INSTA-QT tem estado a fazer. A todos os estudantes e os meus colegas que acompanham nesta atividade. Bem, este tema é um tema que me fascina. O espaço, já estamos em Angola há cerca de 13 anos, com up and downs, como se diz em português e inglês, e após esse contexto, com a permissão do Sr. Presidente, eu vou fazer um switch para o inglês, porque é aquilo que a organização assim o pede. So, I was challenged to explain how the Angolan space program can enable agriculture. So the exercise that I'm bringing today is to show what we have currently in Angola as a space program and how these projects in these programs are helping to enable agriculture. So I'll ask if you can go to the second slide, please. I don't know how many are aware that today's space programs is not a luxury anymore. It's a mandate. If you look in this map, the only continent, not the only continent, but maybe the continent that is using less in space is Africa. Out of, if you see in this map, out of 55 countries in Africa, only 13 are currently using space to solve challenges of the 21st century. If you see Angola, it's one of them. I really love from the organization, if you have any mic that is mobile, it really will help me because it's quite tricky. Yeah. So if we check in this map, Angola is proud to be among the 13 African countries with space programs. 10 years ago, we were not in this map. I think the government did a very good job on coming this map. And as well, I don't know if you know, but at least 11 of the SDGs depend on space. Means that according to the Africa Union, if governments in Africa, they don't invest in space, we're gonna struggle to really make SDGs a reality in the continent. So one of the reasons Angola is pursuing space is not just inventing a cool technology, but it's really using space to solve some real problems that I'm going to show very soon. So I didn't want to bring the mechanics, but I wanted to bring what space program in Angola is doing. So two main pillars, connectivity. Everything we're doing here, even the research the ISPTEC is doing, how we're gonna make it accessible for people who are living in Moshiko, Jamba, in remote areas. We need to have connectivity. Statistics shows that only 33% of Africans are connected to the internet. There is a lot of work to be done. So meaning that we still have 77% of population in Africa not connected to the internet. So if we don't solve this problem, we won't be able to share the knowledge, information that we're creating currently. Second is, one of the challenges in Africa is lack of data for decision making. In space, we have four types of satellites, but I'll focus today in two of them. One, like ANGOSAT-2, that we have in orbit today, is for communication. And then we have a second category, which is Earth observation, meaning that when we see this globe, floods, agriculture, the Earth observation satellite, it can map all these. Thank you so much better. So if we see in this globe, you see that Earth observation satellite actually can map droughts, agriculture, and it's very useful to help governments in tackling challenges with SDGs, like SDG number 2, and we'll just see in a second how they can support. So when we look for the 17 SDGs, we have in continuing connectivity. Today, ANGOSAT-2 is not a myth anymore. I don't know how many I've heard about Connect Angola. Connect Angola, we're using ANGOSAT-2 to take communications on those places in Angola where mobile operators are not there. It's been working. Everybody would like to have more information, how to acquire, to have access. You can come to GGPN, and we're going to show you how. So quickly, Tech Agro is something we are very proud because it's the solutions we design internationally. We even published a paper about that, which is mainly estimating crop And we use a specific case study here in Angola for Unicanda farm in Malange. The research collaboration was done through the ISU, which is a very renowned university worldwide, focused on space. I was the co-supervisor, and Dr. Tejimula was the main supervisor. And actually, Alexandra Lisoba is a very interesting student. She has already a PhD, but not in space. So she went to the ISU to do the master's in space. She's actually Canadian and French, and the fathers are from Congo. So she wanted really to use space to solve SDG 2 in Africa. Of course, the French Space Agency also supported us. Okay, what is the contest in terms of agriculture? This is just giving a little bit of data for the potential of agriculture in Angola. There is a huge potential in agriculture, right? If we remember, the president, while he was here, he mentioned on the problem that drought can bring to farming or agriculture. So one of the reasons why satellite is important, they can assess very quickly what is the conditions of the soil and give information to the farmer on what actions to take. Some of the contest is maize. It counts for between 30–40% of what we do as main agriculture. The land that we need to do agriculture is quite big. We are seeing about 57 million of hectares for us to do agriculture, but how can you monitor that? Physically, it's almost impossible for you to do that, right? It's not sustainable. So the problem actually is how you're going to acquire data and be accurate when you're doing in such big areas. For instance, in Angola, it took us more than 2 to 3 years to do the census, time consuming, right? More than 1,500 people doing this work to collect data about agriculture. And most of actually surveys, people don't really even use GPS to map the agriculture field. So how do we solve this? Still on the consequences, if we don't help to map the agriculture fields, doesn't matter how much investment we did to the farmers, they're not gonna be efficient. So that's why we're bringing the solution. And the solution is Earth observation for agriculture. How we do that? Or how can actually Earth observation help agriculture? Well, we can inform. If we have someone doing agriculture and has like 1 million of hectares, we can inform him very quickly on what is happening with the crops. We can also give almost real-time information what is happening in the crops as well. And of course, we can prevent one of the major problems today, which is food security. So how did we really implement it? What was the demonstration behind? So this is the beauty about space. You fuse with a lot of emerging technologies. One of them we use is AI, or machine learning, if we can say, to help us really map all these crops, maize crops. So what we did in Unicanda, because we had the ground truth data, I think most of scientists here know this term, ground truth data, then we mapped and say, let me teach the machine learning algorithm really to detect this Unicanda firm, what's going on in terms of crops and maize. So now this is a little bit more technical. Very rapid, just a high level is we use different machine learning algorithms. I think most of scientists know that if you really want to make a robust model, You rather use different machine learning algorithms and then compare the performance and pick the best before you can implement. This is what we did. This is a famous pixel-based classification. For those on the space area, is when you're dealing with satellite imagery, but I won't go deeper here. Okay, so this is Unicambe, this side, right? 2,650 hectares. So we ran 4 different machine learning algorithms to see if they could replicate that area or that image. And if we see, we have, all these machine learning algorithms, those abbreviations, and the best one was the random forest, which using a kappa coefficient, which is a very famous coefficient in statistics as well, it gave us really a good result. Okay. So, did I jump too fast or what happened? Let me go back. Okay, I think, yeah. So, and we publish, I think we are in academia, we know, you just don't do a work for the sake of doing, right? You take your research, you put out there, and ask for a peer review on your article, right? And we were able to get accepted and published on the biggest conference in space. We call the IAC. It was held last year in Baku. So we were really proud, and actually I was not able to go there. One of the guys on my team is here, is the one who presented, which is Porter. So really to finalize, I don't want to be long, is really saying that this is remarkable because we can use these results now to start implementing. Actually, we started this project because the Agriculture Association of Angola came to us and said, we need you to help to detect crops and predict yield in agriculture. It's an important tool for decision making. What are we doing next? That's why we're bringing here in the discussion is to see how with the ISPTEC we can continue implementing, right? The model we do, we as a space agency, we don't do research, it's the academia. That's why we went to France. Now we want also to see if we can do here with the ISPTEC and make the model even more robust. Okay. Where am I pointing? Okay, perfect. So we did crop mask generation, crop differentiation. We also done, due to the time I won't get into there. We are doing yield estimation, and we're gonna be doing the prediction soon. And I hope we can have ISPTEC on board as well. So thank you so much. This was just an example on how today the Angolan Space Program is supporting important fields in the country, like agriculture. Once again, thank you for your attention.
Okay, thank you very much, Dr. Zolan. Something will happen. We're going to do some switch off because we would like to connect another speaker. But at the same time, Dr. Marcel, if you can allow us. Please, Dr. Marcel, if you can allow us, we can collect maybe 2 or 3 questions, and we're going to ask Professor Zolana to take a seat, please. You can use even this microphone. It was amazing presentation. We're going to clamp after giving some answer because we have question to ask. Sorry, if you are not understanding, or you understanding, but you have a difficulty to ask a question in English, you can ask in Portuguese. We're going to allow you. We have 2 or 3 people. If you have any question, raise your hand and we'll go straight away, please. Yes, Professor Teresa. Sorry, Professor, as we are broadcasting, I think they're not going to capture the sound. If the technician, they can provide another microphone, please. Or we use that one to save the time.
Thank you very much. From what I heard just a little bit, I think it's very interesting presentation, but I missed it because I wasn't here. I was sorting out things in the background. But then my point is, I want to understand a little bit more if you guys work with a sensor or monitoring the farming, because I know, like you said, you guys are not researchers. You're working more in monitoring. So that means that we can look here a way of combining. And if my work is in research, you guys are monitoring, would be interesting if we could do some joint, some joint projects. Can somebody give me some water?
Yes.
Thank you. Sorry about that. Combine, doing some joint project, because I think it looks very interesting and is jeopardizing. You have to go to France to do the research when we can do it here, and then we are agriculture potential countries. So I think it's a time that we should join and then do it here. So I don't know what you think about doing joint project with ISPTEC. Here in ISPTEC, I know that there are people that relate to agriculture, but my person, I have some project that I've always been looking for people that work with sensor. So I feel like this is the opportunity for me to be able to join a project. What do you think about that? Well,
Okay.
it's not really a question.
It's a discussion.
Yes.
It's a discussion. Maybe to save the time, we can...
So, yes, yes, Professor, this is the reason we brought this presentation, is really to provoke, and I think with President João Fernando, I believe, and we discussed a little bit, I believe we will push this as well to see how we can work with ISPTEC. So you're right, so if we went to France in order to do research with them, we publish papers, and I believe ISPTEC is just around the corner. It's actually 5 minutes from our headquarters. So I think the idea is we can transfer all this experience to ISPTEC and collect, as you say, the research-based census experience as well. Because as I said, we still have next steps for the project and to be deployed. And this is just a piece of what we're doing. This is much bigger. We are now working with the European Space Agency as well on a model that will be a statistical tool officially for census in agriculture in Europe. I think it's a huge opportunity if ISPTEC want to come aboard. I think in Africa they were selected on 3 countries, and we, GGPN, are representing Angola in this project.
Okay, thank you, Dr. Zolana, for the answer. If someone have an answer or you want to join the discussion, what Professor Teresa started, feel free. We are here as academia to discuss, to sort out the problems. Otherwise, we can go to the next question. Okay, let me add to you. I don't know if you have a protocol or not. Let me do it. I'm moderating and also estou a moderar ao mesmo tempo a ser protocolo.
Thank you very much for this a very lovely presentation, and it's very interesting what this program is about. So my question is about the integration of, because I think there was a program of international students from Angola that was sent abroad to basically study geoinformation and subjects that are involved in the geographical systems. So my question is there any kind of program that is put in place to incentivize people to come forward and be part of this nice program as well? So because I think like there was quite a lot of investment that the government has made, and I think it would be quite important for like to integrate like Angolans into this kind of program. So I just want to know if there is anything in place that can like foster this sort of relationship between people who are working abroad or people who are working here but can also contribute and have the experience and also have the know-how to do this kind of program. Because I have personal friends that they are working with this kind of projects, but they are working for international companies. And I think it's good because they have also the experience in working with other environments. So they can bring it back here and then they can also implement. So I just want to know if there's anything in place. Thank you.
Okay, Dr. Zolan, sorry. Let us get another question and then we'll give just the answer once. Thank you for your question. Please, there is any more? Okay, please, let's go.
Yeah, no, this is a great question. Actually, GGPN, for the last 10 years, we never had any consultant. So meaning everything you see there is done by Angolans. So this is the first answer, meaning that all this work is done by Angolans. And some of them are sitting here, actually. So meaning that our philosophy in GGPN is recruit the best of the best. Just to give you an idea, we might be the most graduated public institutions. We currently in GGPN, we have 6 PhDs, at least 22 masters, and the rest are bachelors in the numbers of around 70 people. So just to give you an idea that we really invest a lot in Angolans, first, second, and third. We never had any foreigners and consulted in working with us. So the strategy on answering this is really, this is why I'm here. Actually, this is I came to present to the academia what are the opportunities for students who want to work with us. This is actually some of the actions on pursuing what you're saying. I know it's still slow because unfortunately our mandate is not to do research. We're fusing our mandate in space programs on how to work with research institutions. So what we need is the research institution, they need to come to us as well. But of course, we understand that we have to go looking for them as well to bind these partnerships. And I believe if we do that with ISPTEC and more universities, students will realize, and if you're outside, they, of course, they need to join some institution to be able to do this officially. Okay, that's my answer.
Thank you very much, Dr. Zolan. If no more question, me as a moderator, can you ask? I'm allowed to ask or not? Yeah, it was quite interesting seeing a guy who is a Canadian. The parent, they are from DRC, and he has already a PhD. How he came across to you guys? How he met you?
Yes. Very interesting story. So I come from academia as well. Some of people know me being in academia. I was in academia. I was born from academia. And I really value that wherever we do, we have to involve academia. So one of professors in France, he said, Zolana, you have a lot of problems in Angola, and we have the technology and the knowledge here in France. Send me some topics, and I will see if we can identify students that are interested, because there you don't oblige anybody to work with you. What happened, we send the topics of research, they put on database, and thousands of students go and search. And Alexandra Lizoba when he saw the topic, she said to the university, I want to work with that. Because her story, she's Canadian and French, but her father was originally from Congo. And she understands the challenge we have with food security in the continent. So that's why she decided to work with us and say, I want to make a difference. I want to at least write a paper, build a model that Angola or Congo can use to minimize the food security. Very interesting because she's biomedical, as a PhD biomedical, but she wants to shift the career to space. So she didn't have any problem say, hey, I want to start with my master's, just focus on space. And yeah, it's impressive. A brilliant lady. Actually, a work, she got one of the biggest mark when she finished a master, and now she's employed now with the French Space Agency, just when finished this work. So just to take a few seconds to say, this is also a way to test the quality of the work we're doing in Angola. So we were very proud seeing that.
Well, thank you very much. I ask you that because I wrote a paper on internationalization, and one of the challenges of internationalization, there are many challenges, but my research question is always, why Angolan people, they have a difficulty to be internationalized? But now, trying to find out someone in Canada being under your supervision is a great achievement for our country. Ladies and gentlemen, help me to clamp your hand again for what Dr. Zolan is presenting. Oh, podes aplaudir muitíssimo bem. Thank you very much. Yeah. Okay. Dr. Teresa, you are safe because you are not going now. We're going to receive a Dr. Alan. We do apologize because we're going to try to swift. We have a speaker who is abroad. The technology, they're going to help us to introduce Dr. Alla. But before that, Dr. Alla MacDonald is a head of groundwater at the British Geological Survey, leading a team of 30 staff and an honorary professor at the University of Durban. Many areas of personal research are water security, particularly with a focus on the impact of climate change and the reliance of groundwater system to environmental change. After working with Water Aid in Nigeria in 1999, Alla worked also with BGS in 20 countries and lead the BGS International Groundwater Program from 2011. He has published several books and articles in groundwater, provide advice to the Department of Government in the UK. This is the professor who will present his speech. We're going to ask to the technician if they can help to introduce Professor Alan MacDonald. Sorry, you know that the technology sometimes is a little tricky. We're going to ask you to have a patient. Mr. Alan MacDonald, are you listening, guys? If are you listening, us try to say something. Professor Alan, are you in? We cannot see you, but we want to find out if you can understand what we are talking. Okay. Technicians are helping the connection.
And I've been asked to speak to you about satellite remote sensing for gravity and water for food security in Africa. It's a real pleasure to talk to you, and sorry I am not with you in person.
Okay, thank you very much. We believe that next time you will be here in the person. Now, no words. If are you ready, you can start.
Okay. Thank you very much for inviting me to talk. My name is Alan MacDonald. I'm here in Scotland, where it is snowing and wet and cold, and I wish I was with you in Angola. So I've been asked to speak to you about water for food security in Africa and the use of satellite remote sensing data. So BGS, the British Geological Survey, has got projects all around the world on groundwater. This is a map of where we're currently working with about 20 projects looking at water security in different countries. And you'll see that we work a lot in Africa. So this question of water for food security. Africa is interesting in that it's the lowest amount of irrigation of any continent in the world. So less than 7% of the cultivated area in Africa is irrigated with water. So there's a large potential for increasing irrigation to help food security. But in addition to that, there's still the issue that nearly 400 million people still do not have access to basic drinking water. And this has an impact on the SDGs for food as well as for water, because many of these basic drinking water supplies are used for small-scale irrigation or for watering animals. So in our work around Africa particularly, we have examined groundwater in many different countries and worked with a lot of partners. Many of them are government departments and universities, and we examine groundwater and how to improve individuals' water security. Be that for large-scale irrigation, like pivot irrigation, or be it for rural hand pumps, or finally for small-scale irrigation of individuals and communities. And what we have found in a lot of our research with partners is that groundwater is generally the best way to improve people's access to secure water supplies. The President discussed the big issue of drought. And in a lot of our research, we've found that when people have access to groundwater, they are much more resilient to drought. So increasing people's access to groundwater is a great way of improving their water security and their food security and helping them survive through droughts. So this leads us on to then 3 questions. If groundwater is such a great solution, then we need to find out, is groundwater available? How sustainable a supply is? And will it be safe to drink? So in the time I've got now, I'm just going to talk about the first 2, and then I'll get on to how gravity measurements can help us. So first of all, is groundwater available? And here we look at it at 2 scales. It can be the large regional or continental scale, looking at groundwater at that scale, which can help with planning, can help with the discussions with the banks and the donors and the funders. And we also look at it in a site-specific way. So where is the best place to site a well field? or a borehole, or which communities are vulnerable to drought. And we just had a great talk about mapping crops at that kind of scale. But for this talk, I'm going to concentrate mostly on the regional, the larger scale information. So for about the last 10 years, BGS has been working with partners to develop lots of different groundwater maps for across Africa and for individual countries. So one of the things we've been looking at is groundwater storage. How much storage is available that can be used for irrigation? What's the depth to groundwater? Is it too deep to use? What is the yield? So what size of pumps or boreholes are possible? And then looking at recharge. Is the groundwater going to be replenished, or is it just going to be completely depleted? And lastly, looking at water quality, looking at salinity. And what are the methods that we've been using? Well, to start off with, it's just a lot of it is collating information that's there. Getting maps that have already been developed and hidden away in people's filing cabinets and using them. Also getting together lots of different studies that people have already looked at. But also collecting data from lots of different parts of the continent. And here's lots of different data sets looking at groundwater recharge that we've used. And also monitoring our own observatories, so putting in observatories to look at what actually is happening in the longer term. And of course, satellites. So I'm going to talk about two of the maps first, and then I'll get on to the satellite information that we use. So first of all, groundwater storage. I'm throwing some numbers at you just now. First of all, the overall groundwater storage for the continent is really high. I mean, these numbers, 500,000 cubic kilometres, are more than 20 times that stored in the lakes. It's more than 100 times the annual renewable freshwater when you take out rainfall and precipitation. So we find that storage is high, and even in low storage areas, so these are the light blue areas, the crystalline basement rocks, even in these areas, often there's enough water for maybe a hand pump for several years and to survive through drought. However, if you want to take a lot more water out for irrigation, then that becomes more complicated. So good for drinking water and hand pumps, but when you increase by an order of magnitude the water you need for irrigation, then that becomes more problematic. Then thinking about borehole yield. So that's when you drill a borehole, how much water comes out? Is there just enough for a hand pump, like the picture on the bottom left? Or is there enough for a massive pivot irrigator? And this all depends on the geology. And the map on the right there is a modified map of the geology, looking at the different size of different yields you would get from an individual borehole. And of course, Angola is such an interesting area because of its geology. You've got wonderful geology, very interesting geology, with some sedimentary aquifers, with some basement aquifers. So you've got quite a complicated, interesting geology, which means understanding that can help us understand more about the amount of water that will be available for irrigation. So that's hopefully answered a little bit of the first question. Is groundwater available? And the answer is, well, generally, yes. It'll be enough for a hand pump, sometimes enough for irrigation. So now we're looking at the second question. How sustainable is it? And this is where satellite data from the GRACE satellites can be really helpful. Now, traditionally, hydrogeologists, that's what I am, and I hope there's some other listening in the room. Traditionally, we use what's called a borehole hydrograph to see how sustainable groundwater is. So this map here shows lots of hydrographs from across Africa, and these are kind of annual fluctuations in groundwater level. And you can see some are going up and some are going down. And that's the way that we would traditionally see is the groundwater resource being overexploited. It gives an indication of the local water levels. However, it only gives you information at that one site. There's issues maybe about whether that's representative of a much larger area or not. And this is a study, if you're interested, that we published a few years ago. I've put links to most of the papers in this talk, and hopefully you can see them afterwards if you want to follow them up. So how can satellites help us? And particularly, how can the GRACE satellite and the GRACE follow-on satellite help us? But what this pair of satellites do is they can measure changes in the Earth's gravity over about a monthly basis. So there's been a great innovation since the first satellite went up in 2003. So what they're doing, their first aim is to map the Earth's geoid. You've just got a picture there of the geoid of the Earth. So that's the Earth's gravity field. Gravity is not the same all over the world. It varies according to local conditions. And the only mass in the globe that changes on a seasonal basis is really from water. So our rocks really don't change that amount, even vegetation or people moving around and animals, they don't affect it as much as water. So seasonal changes in gravity can be related to changes in the water cycle. However, it's really good to remember that GRACE has a very, very large footprint. It's 400 by 400 kilometers. So it only tells you average information for a very large area. So there's only several pixels that would cover the whole of Angola. As I've already said, it's got a great monthly return, so you can see the seasonal variation. And also it's good to know that there's been lots of brilliant scientists around the world that take the raw data and do lots of modeling and corrections so that hydrologists like me can use it. So there's a lot of work goes behind the scenes to make these data available to us. So I was going to give you an example of some work we have done for Africa. I must say there's many published studies throughout the world, and you've probably come across quite a number of them. So there's 2 studies that BGS have done recently or been involved in for Africa. And here we've been looking at how terrestrial water changes across the sedimentary basins of Africa. So you can see here what's happening in Angola. And what we do is we estimate the amount of change in groundwater by looking at the total water storage from gravity and take away what we think is happening in the soil and what's happening with river water. And we get what's happening with groundwater. So I'll just go on to the results there. So hopefully this I can talk you through this diagram. But these are the GRACE results, that the change in long-term water storage for all the different basins. So you can see that in the North African basins, there's not much change because they're so arid. And then you can see for the Congo, you can see lots of annual change because of the rainfall, but also some long-term changes. And what this has really informed us is about three different things. The first is that for the Sahel, you can actually see that groundwater resources are actually increasing. Now this is a massive surprise because most of the time we hear statements that water resources are being overexploited, they're being depleted, they're running out. But here we can see, using GRACE satellite, that actually for some areas they're increasing. And that is linked to land use change. That's linked to land degradation, which increases the amount of water going to groundwater. You can also see that here in Southern Africa, where of course we're most interested in now, you can see a more complex variation where the long-term levels go up and down. And what we've done is a lot more research on that to see that that's linked to the global climate. So things like El Nino and other telecommunication events. So we can see that groundwater resources are linked through a lag of maybe 1 or 2 years to these long-term global climate changes. But overall, the story here is that on this large scale, groundwater resources are not being depleted heavily in Africa. There's maybe a little bit up in the Nubian Basin in North Africa, but most of the basins are not being heavily overexploited. And then because we're talking about satellite data, I thought I'd share some other work with you, which is really helpful in looking at the sustainability of groundwater. And here is, we developed a map of groundwater recharge across Africa using lots of individual measurements. These are the dots on there, but also upscaling using satellite data on rainfall and evaporation. And I think for us as hydrologists or hydrogeologists thinking about water for food, some of these satellite products telling us about soil moisture, trying to measure actual evaporation, and also better precipitation is really, really helpful for understanding what's happening to the water resources. So I thought I'd put that in there as well. So just as I kind of finish off now, and I hope the technology has worked okay, I thought I'd bring this together a bit to say, what do these information tell us about water security of individual countries? And here is a sort of very simple framework, which I like very much. It's one I've been using for several years. Basically, it takes these aquifer maps that I was talking at the beginning, looking at aquifer storage on one axis. Then on the other axis, we look at this long-term recharge to the groundwater systems. And we can see that if you've got a large aquifer and lots of recharge, then it's likely that water supplies will be sustainable for some irrigation. But if it's low aquifer volume and not much recharge, then it's likely to be unsustainable. But if you've got a lot of recharge, but a small aquifer, then you can use water in some years, but actually in a drought year or several years drought, if you're taking out a lot of water, it could run out. And on the other hand, if you have got a very large aquifer, but not much recharge, you're probably okay taking out groundwater every year, but in the long term, that will be unsustainable. So this kind of framework I find very useful, and we mapped that across all of Africa and for each country 2 or 3 years ago, and then put it in the UN Water Development Report that came out in 2022. So some of you might have seen this diagram here. So this for each country says the groundwater recharge, how much is replenished, and the groundwater storage. And you can see where Angola is here, where according to this sort of large-scale analysis, yeah, there is groundwater and it is being recharged, but how that varies from site to site, this analysis will not tell you. There needs to be more work. But it does say that looking for groundwater resources and developing groundwater resources more for food is certainly something that should be considered. So that's me finished now. And again, thanks so much for the opportunity to be with you and to talk to you. And just my last points here really are, first of all, that groundwater really is fundamental for water security and therefore for food security across Africa. And we need to think about how that's developed sustainably to help increase food security, both for big farms, but also for small community farms. We find that GRACE and GRACE Following have been really useful tool for looking at water resources. But the scale is a bit of a drawback. You know, we can say that for big areas, but not for individual sites. There are a few uncertainties with the models and how we disaggregate down to groundwater, but generally it's been pretty good. And the last point is the aspiration to have much higher resolution equipment where we could see over 2 or 3 or 4 kilometers using gravity. And this is where maybe some of the quantum gravity sensors are coming in. If we get to that point, that would absolutely revolutionize hydrogeology and our understanding of groundwater. And I could happily retire. So thanks very much for listening. I hope that's been clear.
Thank you very much, Dr. Allen. Okay. If anyone have a question, we can ask. Dr. Allen from Glasgow, are you ready to collect some questions?
Yes, I'm happy to take any questions.
Okay. Please, any of us have a question? Yes? Please, it's better to present yourself, at least your name, and also where are you working, or even your background, because we are trying to see if we can recruit more people to work on technology of quantic, physics quantic.
Good morning, everyone. Desiderio Bash is my name. I'm a student of Master in Petrol Engineering. And my question is regarding with 3 questions that we can see in your slide, the 3 questions. The second question, I didn't get you well because you give 2 possibilities in long term and short term. Regardless, is this project is suitable sustainable. I think the long term. You say that is possible, and the short is not possible. Can you explain this?
Thank you for your question. It's a very good question, and many people are debating and arguing these questions at the moment. So, generally, with groundwater resources, they are replenished every year. Generally, there is rainfall that will replenish them every year, and there might be some drought years where they don't be replenished, but generally they're replenished every year. So we try and work out with groundwater resources, are you taking out more than is going in? And for most of the places I've worked in across Africa, the question is there's generally more recharge than there is people taking out. So what we need to think though is about how for some aquifers in the very north of Africa, so under the Sahara, there's no normal recharge at the moment. So they're not being replenished. The groundwater is just being mined. And there in the long term, the levels will gradually go down more and more and more and more. So then it's a political decision and an economic decision. Do people exploit that groundwater, deplete it, use it up for agriculture, or do they leave it in the ground for future generations? But for Angola and most places where rainfall is of the order of 750 to 1,500 millimeters, then groundwater generally gets recharged every year, apart from some drought years. So I hope that explains a little bit more. But it's a very live debate about what is actually a sustainable use of groundwater resources.
Thank you very much, Professor Allen. I think no one has more questions. Part of me. Okay, I have a small question. Knowing the reality of Africa, it was easy to collect the data for your study?
So that's a great question, and I've worked in Africa for about 30 years, and I work with I very much like to get field data to validate studies. I think you mentioned that already. So I work with very good partners. So no, it's not easy to get field data. It's always easier to stay at home and work on your computer on digital data, but it's always very informative to get field data. So working with really good partners, partner universities, working with ministries or working with NGOs to get studies, to get field data is always very useful. And field data, they always surprise you. So getting field data, they sometimes don't fit your models. They always surprise you, and that's how we learn.
Okay, thank you very much. Ladies and gentlemen, let's put our hands together for the great presentation from Professor Alan McDonough. We are so happy. Next time we would like to see you here in East. Okay, we are inviting you to go to have a breakfast. It's almost 12. If we don't have a breakfast now, after 12, it's going to become a lunch. And we don't want that. Please, all of us, we can get this direction. We're going to follow the protocol. Protocol, pode nos ajudar? Okay. Let us go, please. And when we come, we will continue. The most of the topic relating to technology, physics, and quantic, it will be in the afternoon. Don't go, especially you are engineering, and we are counting with you. We have 15 minutes, 12 to 50. If we go more, it will be 20 minutes for breakfast. Good afternoon. Good afternoon, colleagues. Yeah, we're going to ask our dear colleagues if you can join us, please. The small group on top, you can approach. Thank you very much. To make more impact, because we are broadcasting it. Okay, I think we can continue with our workshop. Honestly speaking, it's my first time in Angola to see a workshop which is taking place in English, from the beginning till in the end. Even we are not yet in the end. But this is a great achievement. And I believe with this kind of vision, we are going somewhere. And also we'd like to thank Dr. Masil being a co-host of this event in Angola. If today we started in Angola, I believe we can expand it more in Africa, to put maybe 3-4 countries together and to make it bigger. I'd like to receive Professor Teresa Matos, but before that, I would like to read a little bit about our background. I remember recently I was in India and they asked me, do you know Professor Teresa? Today it will be good to present her. Professor Dr. Teresa Matos Mangwangwa Vitor is an Angolan or is Anglo-British. Is an Anglo-British professor, scientist, and engineer who excellent in the area of chemical engineering, process, intensification, polymer and catalysis, microbiology, and renewable energy. She holds a PhD in chemical engineering from the University of Newcastle upon in UK. Since 2008, she was involved in a multidisciplinary project in the intensification of antibiotic. Like myself, my field is a medicine. I have a PhD in medicine. But when we talk about the antibiotic, what we knew before, just Alexandre Flagman. Now, knowing that we have Angolan like Professor Teresa Matos, who made a great improvement in antibiotic, is a great thing for us. If I was you, I was supposed even to plow before the time. Antibiotic producer using micropolymer with Professor Galip Akai and Professor Alan Ward as a supervisor. This inherent material resulted publication in prestigious journal with high impact factor. She also completed a master's degree in sustainable chemical engineering at the same institution in Newcastle. That it was in 2004. She graduated as a BS honor in chemical engineering, attended at Northumbria University, Newcastle, in UK, with the petrol refining and fraction distillation unit project. That was in 2001. In 2009 to 2014, she worked as a research associated at the School of Chemical Engineering and Advanced Material at the University of Newcastle. She was working as a processor and product development engineering at Nutris Ltd in UK. Since 2004, among of her many responsibilities were the production and functionalization of microscope material for the agro-bio process and the separation process, preparation, and presentation of proposal for scientific project management, knowledge transferable dossier with view its making and commercialization. She is currently a lecturer and research at ISPETEC since 2020, where she lectures and supervises undergraduate students. Okay. And she's also a member of the Senator and a life member of the World Research Council and accredited review for the American Journal of Chemical Engineering and invited speaker in several international scientific conferences. That means if you are publicating your article in American Journal, make sure it's not going to be refused because she's there. Let us continue. It's a little long, but it is important to understand who is our speaker. Dr. Victor has received several condecorations and distinctions for the innovative and relevant work for the scientific and the technological development of Angola and the world. Among the order of civil merit of the 8th degree, graduated by President of the Republic of Angola, João Manuel Gonçalves Lourenço, for relevant achievement in favor of the nation, the internationalization, best research reward in area of chemical engineering and biotechnology, graduated by International Society for Scientific Network and the Congress of Science and Technology. In 2022, the International Innovative Scientific of the Year Award for the Research and Academic Excellence in Chemical Engineering Award by the Astra Asia Science, Technology and Research Award Congress of 2023 and the International Outstanding Research Award for Research and Excellence in Chemical Engineering and Biotechnology awarded by ISSN International Science Technology Award Congress in 2023. EESTAC 2003. I believe the achievement of our professor is long, but due to the time, let us to stop here. We can put our hand together to us, Professor Dr. Teresa. Please, pode applaudir bem. O breakfast foi bom.
Thank you, ladies and gentlemen. It's actually a great honor to hear all this presentation about myself. So I'm going to skip presenting myself because everything has been told already. So I'm going to go straight to the presentation. But before that, I would like to thank Dr. Marsilio and the whole team of Quantum Technology for inviting me in this prestigious ceremony, and also the fact that it related so much to the work that I've been doing for more than 2 decades. This work that I'm going to present here actually wasn't myself that I chose the topic. It was Dr. Marsilio that chose the topic. He went to my CV and took that topic. Luckily, it's a topic that is already being patented. Okay, thank you. So as it says there, let me see if we point and then read it together. Synthetic symbiotic system as a soil additive to deliver active ingredient through the plant roof for enhanced plant and crop yield. That's what we're talking here about, finish the hunger. So it's about improving the crop yield. So then the previous presenter, they were talking more about sensors and they talk about water shortage, but all we need, apart from water shortage, we need also to improve the soil because the plant need, apart from the water, need the soil. So that's basically what I've been doing all these years. So as it says there, symbiotic reservoir simulated, although in the title you say SSS, here we call it for the normal day, symbiotic rhizosphere simulated, because we simulate the rhizosphere. The rhizosphere is the region where the plant lives, where they find all ingredients, nutrients that they need. So then we simulate, instead of say synthetic, we're simulating. And the rhizosphere, and symbiotic, because in that area will create a symbiosis between the plant, the microorganism, and the nutrients that are there. So basically, we come up with this material, which is a polymer material, but let's not think that all polymer, they're bad. This is a polymer, but we functionalize it, and it stop being harmful like the normal polymer. Are you with me? So we created this environment to improve soil characterization and provide with the necessary ingredients that the plants need. Also, we design it to create a microscopic environment between between the plant roof. And then we will see this during the presentation. And then we will see here that this material actually has a lot of property. So if we're going to put the plant, because we eat what's coming from the soil. So if we have a harmful environment, basically the plant will absorb and we eat that. So then the material that we are mimicking has to be what? Has to be non-toxic, has to be inert. And then if we want to improve the soil health, it has to be what? Hydrophilic, means that absorb a lot of amount of water for later to release to the plant. If it is a dry land, then means that when it's raining, the material will absorb fast and then release slowly when the plants need. And that is the big issue when we put the fertilizer, for instance. Not always the plant has the capacity to absorb those nutrients. So then when it's rain off, everything runs to the rivers, to the sea, to the water. So let's move to be able to see what I'm trying to say. I don't know what's going on. I'm sorry. So then I want to talk a little bit about the story of the invention. As you know, all started from 2005 to 2008 when I was doing my PhD. And during that moment, I was doing my PhD, a multidisciplinary PhD in the School of Chemical Engineering and the School of Biology. With like they've been said already, with Professor Alan Ward, which was for microbiology, and Professor Gali Pakai, which was chemical engineering. But during that study, you don't decide that, okay, today I'm going to the lab and I'm going to invent something. There's some invention that happens by accident, okay? And I'll be honest with you, that's happened by accident. By mixing, by functionalize the material, I could see the material has changed. I was starting to swallow 13 times more water than its own dry weight. So then, as a student, I ran and I went to my supervisor and I said, Professor, look, this material, because the previous guy that was working in the plant, basically his polymer were hydrophobic. You know what is hydrophobic? It doesn't like water. But for agriculture, you need hydrophilic. You need to love water. So then I made hydrophilic the material without even know it. So all happened then. What happened? The supervisor said, give it to David Berker, because David Berker was working in the plant. I was working what? In production of antibiotics. But for production of antibiotics, I didn't need very hydrophilic environment as the agriculture. So let's pass this story, because it's a long story. Let's cut it short. I don't know what's going on. It's not moving. It's not moving, sorry. I'm not great in this technology, because when I started it, there was no computer when I started to go to university. Yeah, it's not moved. Okay. Okay, then maybe I'm not pressing that much. This is just one of the patents, like I said, from this material, was created 2 patents. One patent was for the material in various applications, including the application that I needed. And the other patent was as the one we're going to discuss today. This way. I'm pressing that way. You see, everybody saw me pressing that way. You change? Okay. Okay. I put it there if you would like to read it, but if you don't, we can pass it. But basically, it's what I've just said it, okay? And then we have this strategy. And maybe some of you already heard about process intensification. It's more headed in chemical engineering, process intensification. It's a strategy that has been invented in the 16th. And I had the privilege to be a student of the person that invented this strategy, Professor Colin Ramshaw. Colin Ramshaw, he believed that with process intensification, you could reduce the cost, reduce some step in the process, and this will bring more economical advantage. So then what happened is we took that process intensification strategy to the agriculture. Basically, I've got here this image where you could see that this is the rhizophasic cycle. So what's happened is inside the plant. So when we produce the material, like we say, is the one to mimic the rhizosphere, then we add in some microorganisms that will be beneficial for the plant. Some of these microorganisms, they're endophytic. Even if they're endophytic, it means that they will go inside. They'll go inside of that design that we saw, and then the endophytic will go inside, will be helping the plant to fix nitrogen from the atmosphere. That's not great? So it means that if the plant needs nitrogen, we really can just fix from the atmosphere by using some endophytic bacteria. And then if the plant need potassium, also we can put some microorganisms that will make potassium available to the plant, or phosphorus available to the plant, because some of these components of the fertilizer, they're actually soluble in water. And being soluble easily can wash out, like I say, it can go to the river. So then if we lock them to this material, means that will be there available for the plant. It's not gonna be washed out. So of all the projects, we start with a problem. So there is a problem to solve. One of the problems just that the the fertilizers get washed by the water. And then what we get water pollution. We get soil degradation. So then the problems are here. And then we need to address this problem. For example, we have here the red one supposed to be the light. Am I wrong? Yeah. No, the light I need to point it to the presentation. No. Okay. Then we have here the river contaminated with heavy metals. No? And then we know what is activity as human activity with agriculture. Agriculture contaminate the waters a lot, not just the industry. Okay? And then we have here also soil degradation. When we have okay, I rather move around. Okay? So addressing this challenge will be with what? Basically what I've already said, using our microporous material, because we lock all these ingredients and deliver when the plants need. You know, the first presenter is from the space, so understand better than I. It's not working. Can someone change for me over there? Okay. So this is the material. So we solve the problem, and then we find here the solution. What's the solution? Development of microporous structure material. That's exactly what I said. Known as a SRS, symbiotic rhizosphere simulated. That's what we said, you know? Then that can be functionalized. Like I said, first is a polymer, but after we functionalize, actually when we functionalize, it stops being hydrophobic, it becomes hydrophilic, and the other properties that we're going to see later, because we will help then the diffusion of nutrients, the diffusion of mass transfer, heat exchanger will happen smoothly, because it's actually resemble like a capillary network. You know, in our lungs, we have capillaries where oxygen can be transferred. So it basically resembles that. That's why we have this structure of a capillary. And that is the material when we look in the SEM, scan electron microscopy, we can see all the pores, and we can analyze what type of the pores we have, what size the pores we have. Okay. As already give you a little bit of the background about the material, then we need to produce the material. To produce the material, we need a reactor, okay? And we know some of us here that is being a lecture of a reactor calculation, probably they know, or even never been lectured, it been a work of a reactor. We know that the mode of operation for our reactor will be semi-continuous, although there is a continuous, semi-continuous, but here we want to use it semi-continuous. Semi-continuous because we will see when I show you the reactor, because we continue feed in, but the outlet, the downstream is locked, it's closed. So we are only feeding, but we are not, until the reactions take place is when we open to collect our product. Then the reactor type that here we're going to use is the reactor non-catalytic. We could also use the reactor catalytic if we want, because we could use, for example, sulfuric acid to act as a catalyst. Number of a phase would be heterogeneous phase, because one of the phase, when we have two or more phase, then we have heterogeneous phase. Because not a homogeneous, not every phase is liquid or every phase is gas. Here we have, although they're both liquid, but one of the phase doesn't mix. And we know, for instance, when we put oil and water, they're not mixable. And then when oil and water are not mixable, what we do? We use the tank agitation, okay? So we use impeller to be able to mix the two, and the emulsion will be created. Basically, this is the reactor. As you see there, we have the vessel, we have the motor, we should make the impeller to work. We have the parastatic pump that will help us to pump the liquid to our reactor. Finally, we got our emulsion, and then we put it to another reactor with 60 degree. After that, what we do, we need to take it to the circlet, basically to wash, to remove all the reactions that hasn't been reacting. Okay? And passing now then to the properties, as you see there, as we saw before, then if we look in a scan, SEM, scan electron microscope, we'll be able to see everything that we can't see with naked eyes. That's why we managed to see that, oh, they've got big pores, what we normally call them coalescent pores. Coalescent pores, those pores that when you're mixing, small pores join together and then they make a big pore. So we don't want too many coalescent pores in our structure. The good thing of this material is that you can control the properties. You can control the pore size. You can control the surface area. And we know the surface area, if the surface area is big, means the pore size has to be smaller. It's inversely proportional. Then we have here, look after functionalization, we're going to look at the material in SEM again. Could we see some crackings? That's good. Those cracking means that even the soil, the natural soil, because what we're trying to mimic is the soil. Even the natural soil has crackings, so that means that there will be diffusion of what? Nutrients. The fusion of microorganisms that are in the environment. And that's what we wanted to achieve with the functionalization. And just to tell you that this material doesn't just have application in agriculture, has also application in tissue engineering. Like I said before, with capillary, it resembles the lung. The lung is porous. So it can be used for tissue engineering, even for bone tissue engineering, because the bone, it looks like a scaffold. If you, I don't know, if we cut the bone, cross-section, you will be able to see pores and they resemble this material, so that we take it as well as a tissue engineer application. Intensify separation of oil and water emulsion is one of the work that my colleague from Malaysia, Zainura, has done, and the result was very achievable, and she was able to submit that as a chapter in one book. And then we have also intensified gas-liquid separation. We have the gas cleanup, which is work done by a girl that was working gasification process. We have also water cleanup. A Turkish guy was working water cleanup using the same material. And then in catalyst, a lot of people were working using this material for catalyst. Basically, for catalyst, what we'll do, we just deposit the metal that we wanted this material, and then the catalyst will be microporous catalyst. That's good, because then when you calcine, all the material go away, and then you have the structure of the metal porous. And then we also work in microreactor. In that case, I was working in the microreactor. I was working intensified bioprocess, which basically to be able to produce the antibiotics. And then finally is the agro-process intensification. David Becker worked on that, and that's also I work during my research associate. I work on that as well, and that's the part of the patent that we're discussing today. I brought you here this. I call it my pulse diagram, basically to describe what we saw before. Basically, we have here the micropore in the middle, and then we have all these tentacles trying to go to different applications. In the health, we saw tissue engineering, production of antibiotics, and then we can go to agriculture, this case is symbiotic rhizosphere simulated. We can go to the environment, which clean up is a separation process, because we can use as a membrane for separation of process. And then energy is also, we can use it to immobilize microorganisms to be able to produce energy. And actually the list of applications going on, because now being here in INSTA-QT, one of my colleagues that is mechanic is actually said that we can do some work for mechanic application as well. So we are trying to test the resistance of the material to see if we can use it for mechanic purpose. Yes. Then that's just to show that is the process intensification, like I said already, related to the agro-process, related to the process intensification. Application and the benefits, we have what? The SRS can be used for various crops, such as these crops that I put there, that's the crop that appear in the patent, such as cereal, leguminous, vegetable, fruit, and flowers. But in reality, when I came here in the SPTEC, we also try with different crops. We tried with corn, we tried with tomato, we tried with okra, and we had our little greenhouse there at the back. I don't know, some of the colleagues probably remember we used to have the greenhouse here where we are testing the material here in Angola. We didn't want just to have a result from the other geography, so we had to do it here in Angola as well. So during the process, like I said, all the physiochemical properties can be changed. So basically, we can make it more elastomerous, we can make it more porous, it depends on the application that we are interested. We can make it more hydrophilic or more hydrophobic, and so on. That's the beauty of work on this material. I think I'm never gonna work another material anyway. So here, some culture that we test. As we saw, we test cocoa in Colombia. We test coffee in Colombia as well, and in England. So then there's some results. If you look at here, it's gone. Okay. If we look at here, the first plant, very small, that's without SRS, and it was the only one that survived. And the beautiful thing is, I wasn't the one doing all these tests. These tests were doing, like I said, in this geography, I wasn't there. So I was just sending the material for them to test, so to have a second opinion. I think that's the best way of doing things. And then you could see the biomass of the plant, a lot of growth of the roof. That is a sign that the plant is happy. So we are simulating the environment. Let's go quickly. Okay, here we did some testing in England of miscanta, because miscanta is like a grass, but it's a grass that uses for biomass, for energy. And then it grows in cold countries, like originally it's from Poland. And then we grew it in England. We did manage in Bellsbrada to make some Bellsbrada is a nursery where we do the plants, and then you could see there with the SRS, without the SRS, we could see definitely photosynthesis wasn't there when SRS wasn't there. So there's nothing really to say much. And then here we have different grasses as well that have been tested in different conditions, just with the blank without SRS, with SRS, only with SRS with Aspergillus. Aspergillus is another endophytic that fixes nitrogen, and then SRS with grass of a mycorrhiza. Mycorrhiza is a microorganism that grows in the rhizosphere, so normally making nodules to the roof of the plant. And then we have here banana that has been done in Indonesia and in China, but I didn't manage to get the results from China. Okay, I only got it from Indonesia, and we could see some of us, we don't know that the bananas, they're dying. Bananas, they're being affected by a fungus called FOFO. So if we don't solve this problem, there'll be a time that we're not gonna eat our source of potassium, which is banana. So then we could see, as you see, that it's being affected by fungus, and the inside of the stem is actually dark, and then when it's with the SRS, it's all clear. So the picture probably talks more than myself. Okay, this is some field trial in Colombia that has been done with palm oil, and then also with different conditions of SRS1, SRS2, without SRS, and without no doubt, the result with the SRS were much better. And I wasn't there again. Okay, and then also, like I said, with Miss Kanta, we did in Bell's brother. Now Bell's brother took to the field because Bell's brother first do the growth in the nursery and then after takes to the field. What happened there in the field? You could see with SRS. This is the time of the Everest. You Everest them when they're dry because it's for making biomass for fuel. So then with the SRS, definitely, I'm not gonna say that much. You guys can see with the SRS, without SRS. Again, was a second opinion. I didn't done this test. Okay, this is the test that we did here in Spetec with the students. Some of my colleagues here remember that I managed to recruit more than 30 students from chemical engineering that they've already now finished. Some of them they've already defended at this essay. And then we also, image can tell you what happened there. Although we are not from agriculture background, we try our best because we just wanted to test the material. Therefore, that's why probably the area wasn't very well organized the way it should be if it was someone that with an agriculture background. Then we also managed to have okra. I did eat the okra from here. I did eat the tomato. We planted also passion fruit. I didn't manage to eat passion fruit because the student they took passion fruit. So it means that I'm still here, nothing happened. The result was good. So I'm almost finished now. That's just to show you how happily the roof hair are inside of the material. As we see there in the top of SEM, actually the roof hair penetrates inside the material looking for nutrient. And what is inside the material? There's nutrient, okay? And then that's why the plants grow happily. Then we can see here, this is grass association, how it looks. That's a soja. I brought soja from UK to grow it here in Angola, but I didn't manage to grow there with the student. Soja didn't want it to grow. Yeah, that's what happened. And then also here, we took an SEM, the SRS, we cut it to the cross-section to be able to confirm if the endophytics actually they were in the SRS or they translated to the roof hair. Because as we said, endophyte, they're meant to be living inside of the plant, but they're benefic. They don't do harm to the plant. Actually helps the plant to fix the nitrogen. So then we confirm of the SCM, as if you see here in red, that's the bacteria that we inoculated that were inside. And then here we have some Mescanta result from Bell's blood, where you see A and B, they are with SRS, and then control 1 and control 2 without SRS. So A, which was that trait that I show you without SRS, with SRS, was much, the growth was unbelievable. Was very tall, and we could see that photosynthesis took place. But then what happened, the leaves, there was not much difference in the leaves. The amount of the leaves, we couldn't see much difference. Can you see? So maybe the responsible of the leaves, because each nutrient in the plant has a responsibility. Some they're responsible for give good biomass in the roof, some of with the leaves, some of making the leaves very green. So responsible of amount of the leaf probably wasn't there in our material. Makes sense? But we could add in because it's very flexible, very versatile. So this is the ongoing work that we are doing here with the resistance of the material in the lab with colleagues from mechanic. So we're trying to take it there, the young module, to see the elasticity until by putting force to the material until when the material will break. And I hope this will give us a paper to be able to publish our work. I think we just finished. This is just the conclusion, which I probably am not going to say the conclusion because I've been saying it as I was going. So then, just to show you finally some references that became from the work. Yeah, that is the reference that came from the work. And then finally, Okay. Okay. That is the letter that I received from Newcastle University because there was a problem with my second patent. My supervisor put David Burke in the patent, but he never put it me. And then in 2014, when he left, I had to be with the responsibility to do the work that he was doing, to submit all the work that he did. In my research, I discovered this patent. I read through the patent and I could see all the clauses. That's the one that I wrote to give it to him, but he didn't include my name. But in God's grace, I won the case and they included my name. So it means that when the patent was filed, my name wasn't there. But when the patent was accepted, my name was there. Thank you very much.
Professor, can you take seat? And you can also hold the microphone.
Sorry, I'd like to thank these people the support that I received, because without the support from the UK government, nothing this could have been possible, because my PhD, my undergrad was from Angola government, but my PhD was from British government. So thank you very much.
Wow. Okay, let us go straight away without of mixing with the Professor Americo question. If you have a question regarding Professor Teresa Matos, we can ask straight away. Myself, I have 2 questions, but I would like to collect yours. Okay?
Good afternoon, Doctor.
Good afternoon.
I am José. I would like to speak in Portuguese because I have a little difficulty to speak in English. Can it be?
But can you understand? Feel free. This workshop is in English. If you want to challenge your English by yourself, continue. Even with mistake. This is the way of learning.
Yes. No matter. I would like to relationship about the pH. pH is the most important property of the soil, is plant. I would like to relationship to pH. Yes. Yeah, about the impact of the environment. Yes.
Please, we can applaud for Mr. José. You did well. We understood what you wanted. This is the way. Well done.
Thanks so much. Thanks.
This good question. But if you remember when I said that we mimic the natural environment, that means is mimicking for everything, including the pH. That's the pH you refer, pH, no? pH, yes. Including the pH. So if we are mimicking, and we know in the normal environment, the pH that the plants grow is a 6.9 or 7, then means that our material, we need also to adjust it because we say it's versatile and we can easily change its property, including pH. But then with the pH, we need to be careful which base we're going to put, because we don't want to mess about putting sodium hydroxide, because we end up to leave a lot of sodium. Okay. So then, what is the base, the acid, the base that we're going to use? Probably we use ammonium hydroxide, because whatever result is will be what? Salt and water. Ammonium sulfate plus water. Am I wrong? Chemical. In the chemistry point of view, you don't want the result to be harmful to the environment, because what we're trying to do is solving the problem of the environment, so we can't bring another problem. Okay?
Okay, thank you very much, Professor. Let us go to the second question. I hope that Mrs. Jose is clear.
Are you
Did
happy?
you? Are you happy? Good.
Mr. Desiderio, once again. So I could like thanks the beautiful presentation that we all saw. So my question is, all that country that you send the sample, I could like see during the presentation, they are all tropical countries like England, Thailand, and China.
England.
I saw. England
England is not tropical.
is not tropical.
Is it cold?
It's a cold. Yes, yes. But my question is, did you send some kind of sample in different environment like desert? So here in Angola we have Namibia province. The environment in that province is like a desert. I could like understand if we have some kind of study in this area.
Yeah, that's good question. That's good question, and then because what was in our plan. I did my PhD, I invented this material, but then after finish my PhD, I was then work as a research associate. That means that I continue do some investigation this work in Newcastle University. So then, because Newcastle, England is not a tropical country, so then we had to start to send sample to a tropical country until I got tired and I say, my country is also tropical. I'm going to take the technology to my country, okay? But there was the purpose of sending the samples to Dubai because Dubai wanted to grow grass. That's why we had some experiment trying to test in the grass. So it means that in the nursery, we could see that the grass grows happily in our material. So that means the next step could be field trial, send it to Dubai. But then what happened? My supervisor stopped working for Newcastle University, and then the project died there about taking the sample to Dubai to try to the desert, okay? So, but the question is very good, because then you open me my window, because we have desert here in Angola. Yeah. Where can I go? You made me you clicked something that was dying, or wasn't dying, was sleeping, was domed. So now you click it, I'm going to do that. Thank you for your question.
All right.
Thank you very much for helping to the resurrection of something which was dying.
Yeah.
To Professor Teresa Matos. One more question. Okay. I have just small question, Vice President. Professor, you say that you brought some soja from Newcastle, but it could not grow in Angola. Why?
I don't know. And the students should be here to answer. Maybe the environment of that soja, or maybe that soja was genetically modified, and then growing things genetically modified is more complicated than growing things that are not genetically modified. Because non-genetically modified, they grow like, let's see, like Jimboa. Easily they grow, you know? But when they're genetically modified, means that you have to follow pé da letra, como se diz in Portuguese, all the steps for this. Then since I didn't have the protocol to do it, we were just doing it here in this spectacle with the students. And I said to the student, let's try again. And then they said, professor, I didn't grow. I said, let's try again. Hey, professor, mesmo gosta da soja dele, until the soja go rotten. So if it go rotten, if before go rotten it wasn't grow, after go rotten, what's the point to put it in the soil?
That's fine, Prof. We understood it did not grow. And also you said that you planted something, the students, they eat it without of giving you. I don't know why.
It was a passion fruit. And even my colleague was here, that she's a nurse. One day she sent me a photo. Professora, your passion fruit is actually growing beautiful, but I wanted to take it to give to you because I know you are doing it for research, but it's still a little bit green, but it's big. I said, let it stay good. But Professor is gone.
I ate it.
Probably, I don't know, the student or another staff took it.
Okay, let us put our hands together for greater presentation. Thank you very much. I hope that you will come back to the next time when Dr. Masil is going to host another event similar to that.
But then what I would like to see here is actually the symbiosis, the multidisciplinarism about our project. Because when I won the prize, my first appeal that I was doing to everyone that I wanted to work with a census. Now today I hear here that you guys work on the census, so nobody answered me in that moment that, yeah, we can work. But now that we are face to face, you know, when you're speaking to someone face to face, you can't say no. So what I wanted to see is us joining together and do a multidisciplinary project for production of antibiotics, for agriculture, for catalysis. All these things need census. Thank you very much.
You're welcome. Thank you, thank you. I hope that you are enjoying it. Well, I would like to host the last speaker for this section, but before coming here, I will give a briefing about his CV. The next speaker, it will be Professor Americo D'Amata Lorenzo Vitorino. Professor Vitorino, actually, he graduated, he studied geology at University of Agostinho Neto, Faculdade de Ciência, in 2001 to 2006. He achieved his master's degree from Instituto Superior de Estatística e Informação, Universidade Nova de Lisboa. He started from 2009 to 2011. Currently, he's doing his PhD, also in geology or applicable engineering at University Agostinho Neto, Faculdade de Ciência. Professor Americo is the administrator of ELG, which is the Institute of Geology. L is Luanda? Please, Professor Cyril, help me. LGL. A. Okay. EGO. Okay. Part of that, Professor Americo is a professor at ISPETEC. That means he teaches here. He's one of colleagues. His CV, if we continue to read it, it can take us even 2 to 3 hours, because he does research, he has a lot of publication, even is the author of the books. He has a chapter of some books, and he has 1, 2, 3, 4, I can see a lot of articles. And also, he participates a lot of time to the conference. He has been even in Madrid, and also is publicating some articles over there. Please, when Professor is approaching here, we can put our hand together to welcome him. Welcome, Prof.
Boa tarde, excelentíssimos colegas, membros da direção do ISPETEC, colegas meus do Instituto Geológico, né, que se fizeram presentes aqui hoje, estudantes, alguns deles até já foram meus estudantes. Vamos suavizar aqui um pouco o inglês, vamos falar num idioma mais fácil de nos compreendermos. Né? Falar português é mais fácil. Né? A professora Matoso gosta de falar inglês. A nossa apresentação, na realidade, é um pouco alinhada aos objetivos do evento. Um título bastante sugestivo, a natureza geológica dos solos angolanos e países da África subsaariana e a sua distribuição das bacias, a distribuição das bacias hidrográficas para a agricultura. É bastante amplo. Se calhar tudo o que se falou aqui passa por este tema, direta ou indiretamente. E por que é que nós nos sentimos à vontade em abordar essa questão? Nas vestes de administrador para a área técnica do Instituto Geológico, nós vamos fazer a apresentação fruto do trabalho que vem sendo realizado nos últimos 10, 11 anos, com forte apoio no Plano Nacional de Geologia. Toda a informação que nós vamos passar resume-se em mapas. E estes mapas estão todos disponíveis no WebGIS da instituição, que todos os participantes com esse código QR poderão acessar facilmente a esta plataforma e verem com maior detalhe aquilo que nós vamos aqui passar em breves minutos. Não vamos fazer 45 minutos como a professora Matoso, porque a professora apresentou quase metade da tese. Nós vamos só apresentar uma percentagem daquilo que foi feito durante os últimos tempos. Então, o que é que trazemos aqui? Um enquadramento, um pouco, e vamos recuar, né? Para quem não esteve aqui, estiveram aqui colegas da Agência Espacial que trabalham com o nosso satélite, que recolhem dados, e falou um pouco da importância do centro para o desenvolvimento do país. Nós aqui pegamos mais as coisas e tornamos elas mais visíveis, né? Saímos só da conversa de satélites e entramos um pouco naquilo que é o intro, ou seja, o filé mignon dos produtos que esse satélite gera. E a questão é exatamente esta. Por que tanto investimento? Por que estas imagens são tão importantes? O que é que elas nos permitem fazer? Como é que elas se relacionam com o tema que está aqui a ser discutido? Que benefícios ela traz? E aqui vamos tentar desmistificar um pouco a questão. Por isso é que colocamos aí cartografia prévia. Porque, por serem imagens de satélites, elas nos permitem pré-definir alvos. Mas nada melhor do que o dia a dia, a prática, como se diz na gíria, a mão na massa, para darmos nomes às coisas. As imagens de satélites permitem observar, mas quando quisermos tocar, temos que ir lá. Então, nós usamos as imagens de satélites para cartografar previamente, ou seja, fazer um trabalho de gabinete e logo depois ir a campo com esse trabalho mais ou menos avançado. Por isso é que temos a cartografia, logo depois temos os trabalhos de campo, que são muito apoiados nessa base cartográfica, ou nas bases cartográficas, porque são várias, e depois vamos ver aqui alguns resultados, e como disse, eles aparecem todos expressos nesse WebGIS, que hoje é a forma mais tácita, mais prática de se publicitar aquilo que nós temos disponível para o nosso público. Estamos a falar do território nacional como tal, não vamos sair do território, o tema até nos pedia que o fizéssemos, mas para não cansar, nós decidimos andar um pouco mais por aqui para conhecermos melhor o território em que pisamos. O que vamos fazer é tentar compreender como é que com essa tecnologia espacial e com trabalhos de campo nós elaboramos e validamos os mapas de solo, elaboramos e validamos mapas geológicos, e elaboramos e validamos os mapas hidrogeológicos. Aí sim, com essas três bases, achamos nós que estamos em condições de avançar para qualquer outro projeto que visa produzir mais tomate, produzir mais milho, produzir mais soja, o que for. Ou seja, se nós não tivermos isto organizado, por mais vontade que tenhamos, nós não conseguimos aumentar a nossa produção. Então vamos falar desses três produtos. E eles começam pela elaboração de um mapa prévio. E os mapas prévios são elaborados a partir de imagens de satélite. As imagens de satélite são geradas por grandes empresas internacionais, multinacionais, sobretudo a NASA, entre outras, que vão ao espaço e fotografam o universo e nos disponibilizam essa informação. Temos a sorte delas serem à escala que estamos a conversar, de forma gratuita, porque estamos a falar de cartas geológicas, cartas de solos, que vão até a escala 1 por 50 mil. Se quisermos melhorar essa escala, temos que entrar em satélites do tipo Kickbirds e outros, e aí já temos que fazer um investimento maior na obtenção de imagens. Mas para aquilo que se aplica, que é a elaboração da cartografia de solos, esta cartografia, estas imagens são mais do que suficientes. É assim como nós a vemos quando vamos a qualquer página web, sobretudo americana, com apoio da NASA, baixamos uma imagem destas tem 7 bandas, hoje já tem 8. As bandas respondem ao espectro eletromagnético, cada imagem observa um alvo determinado. E é com a mistura e a combinação destas várias bandas espectrais que nós conseguimos diferenciar um alvo do outro, um mineral do outro, um tipo de solo do outro, água turva de água limpa, água que está a ser submetida a operações de garimpo e água que está com uma fluidez normal, como naturalmente ela é gerada. Porque estávamos a falar do país todo, tivemos que pegar e baixar as imagens do país, fazer combinações de bandas e tentar aqui obter o primeiro produto que nos leva a campo, que é o mapa prévio, no caso, e já avançamos um bocado. Está a recuar? Sim, senhor. Quando pegamos aquelas imagens, porque elas vêm por aqui, tem esse conceito. Acho que a maior parte das disciplinas aqui no INSTA-QT, no Departamento de Geociência, tratam de sensoriamento remoto. É a arte de visualizar coisas à distância e hoje nós fazemos com as imagens de satélite. Essas imagens são adquiridas da forma que anteriormente disse. Fazemos aqui uma fotointerpretação. Nesta fotointerpretação, nós classificamos os vários tipos de solo que se apresentam, são reclassificados em parcelas, com níveis de classificação mais afinados, que foram ditos aqui, alguns deles, pelo nosso primeiro preleitor do Centro de Dados Espacial. Fazemos aqui algumas análises dos componentes principais, fazemos a classificação supervisionada e, no final, nós obtemos um mapa que é a figura de solos, que é a figura geológica, que é a figura litológica que nos leva a campo. Enquanto nós fazemos isto, nós vamos pegar uma zona como exemplo do país para tentarmos perceber como é que chegamos a todos os produtos finais. E por que pegamos essa zona? Porque mais à frente vamos dar um exemplo prático dos objetivos que nos levaram a fazer essa apresentação para o dia de hoje. Nós aqui vamos falar um pouco da bacia de Kalahari, que é uma bacia que está sobre a província do Cunene, sobre o Namibe, sobre o Quanacubango. Aquele ambiente geológico extremo, ou as cheias, ou as secas, e quando há um ou outro, nós temos que tentar resolver o problema. Ou seja, é uma das regiões de Angola mais complexas de se discutir, mais complexas de se fazerem projeções para serem sobre elas aplicadas qualquer política de desenvolvimento. Então, nós pegamos aqui estes pequenos retângulos, estes pequenos quadrados, essas pequenas figuras geométricas, para mostrarmos como é que nós classificamos aqui os solos. Esta imagem tem data, é uma imagem que tem quase um valor inferior a 10% de cobertura de nuvens, ou seja, ela é visível, nós não temos objeções nenhumas. Quando nós olhamos na janela do avião, ali no coisa, olhamos e vemos nuvens, não conseguimos enxergar o que está por baixo. O satélite faz a mesma coisa. Se vemos nuvens, ele não enxerga o que está por baixo. Logo, a imagem não nos consegue trazer os dados de baixo. Temos que trabalhar com céu limpo, com imagens nítidas, para poder obter a nitidez que aqui se apresenta. E aqui nós combinamos, como disse, 7 bandas do espectro eletromagnético, onde cada banda nos conta uma história. Ou seja, a combinação de 3 bandas dá-nos sempre uma cor diferente do alvo. Nós vamos observar isto agora com esta cor, podemos não compreender melhor a sua forma, mas com outra combinação de bandas, com outro conjunto de imagens, nós poderemos enxergar melhor aquilo que queremos ver que aqui se apresenta. E com estes algoritmos nós vamos avançando e vamos obtendo resultados. Aqui nós estamos com uma banda 432, que é uma banda do visível e 2 bandas do infravermelho, um do infravermelho próximo, outro do infravermelho distante. Queremos fazer um mapeamento a 1 por 100 mil, queremos observar melhor isto a essa escala, porque é esta imagem que depois nós vamos transformar em mapa. Ou seja, para pintar um mapa, na realidade, é o ABC desta imagem que vai nos dizer como é que esse mapa se apresenta. Aqui temos uma cor, aqui temos outra cor, aqui temos cores mais escuras, aqui parece termos o mesmo ambiente que temos aqui. Então, para termos de solos, quando falamos de espectro, aquilo que é igual tem o mesmo valor em pixels. Aquilo que é diferente tem pixels diferentes. Significa dizer que cada cor aqui deverá ter um pixel. Cores iguais, mesmo pixel, mesmo número de pixels, cores diferentes, pixels diferentes. A mesma imagem, se nós combinarmos com outros valores, nós vemos a mesma coisa, mas de maneira diferente. E se combinarmos com outro valor, vemos a mesma coisa de maneira diferente. Este corpo que está aqui é este corpo que se apresenta aqui. Fizemos um zoom, não melhoramos a escala, só fizemos um zoom e o que aparece é esta estrutura que aqui está. E começamos a diferenciar plenamente bem do que é que estamos a tentar desmistificar. Estes camaradas vão gerar um mapa geológico, porque nós não começamos nós não inventamos, as coisas já estão mais ou menos feitas. Angola tem mapas das décadas de 60, de 50, de 40. O problema é que esses mapas foram gerados com uma tecnologia diferente da que nós hoje temos disponíveis. Então, o que nós fazemos é pegar nas cartas que existiam e atualizar essa cartografia por aquilo que existe. Utilizamos aqui essas imagens de satélites que nos dão bem a permissão de fazermos esse exercício. E aqui eu faço uma sobreposição. Os colegas vão observar isto, nós chamamos contactos, porque esse corpo amarelo representa uma litologia diferente deste corpo azul, e assim sucessivamente. E se nós observarmos, sobretudo aqui nos contactos, os colegas, eu vou colocar uma imagem de satélite por baixo, a subir lentamente, e vão ver como é que nós transferimos o que está no papel para uma atualidade. Ou seja, estamos a cartografar o que vimos antes na carta geológica real, feita há décadas, com aquilo que temos hoje que podemos melhorar. Então, nós vamos fazer uma sobreposição e vamos ver como é que os corpos aqui vai se redesenhando e vai obtendo a forma real. E nós corrigimos o mapa que tínhamos anteriormente pelo mapa novo. Saímos de uma escala de um mapa, a escala 1 por 1 milhão, e vamos a um mapa, a escala 1 por 100 mil. Isto é o modelo digital de elevação. Isto são as cotas baixas, cotas altas. E aqui estamos com zonas altas, como indica o modelo, e aqui estamos com zonas baixas, ou seja, as linhas d'água passam por aqui. Se quisermos pensar em falar em bacias hidrográficas, temos que olhar para esta imagem, que é uma imagem que também obtemos via empresas como a NASA, como disse no início. E vamos fazer a mesma coisa que fizemos na passada. Vamos colocar aqui as imagens de satélites, que é uma fotografia real, ao MDT. Quando nós sobrepomos a imagem de satélite da área por cima do MDT, nós obtemos a fotografia da cidade em três dimensões, porque esta é uma figura tridimensional e o mapa que estamos a falar é um mapa de 2 dimensões. Quando nós fizemos o mesmo exercício, o que vai acontecer é exatamente isto, ou seja, eu estou com a imagem real por cima do modelo digital tridimensional. E começo a dar nomes. Os colegas vão ver que agora já tenho corpos com códigos que parecem ser isto, que neste momento podem significar única e simplesmente códigos, mas que representam cores, comportamentos diferentes, cores diferentes dos pixels de cada uma dessas imagens. Os colegas também sabem que as imagens são um conjunto de pixels, né? Pronto. Pixels e pixels fazem uma matriz e aí nós temos a imagem. Quanto maior o número de pixels, maior qualidade tem a imagem. Está a funcionar da mesma forma aqui. Imagens com alta densidade de pixels são imagens muito caras porque têm uma resolução bastante elevada. Os nossos iPhones e tal se diferenciam nisto. Eles têm a tecnologia que têm, mas o valor deles está na câmera. Ou seja, o pixel resultante daquela câmera é que atribui o preço à tecnologia que o telefone tem. E é disto que estamos a falar. Portanto, quando nós olhamos para essas coisas, começamos a ver que isto, na teoria que eu anteriormente mencionei, isto parece ser a mesma coisa. E como nós aqui conseguimos ver que é a mesma coisa, nós atribuímos o mesmo código. Significa dizer que quando formos ao campo, não precisamos visitar esta área. Vamos visitar esta área e vamos tirar aqui 5, 10 amostras. Vamos visitar esta e vamos tirar aqui 5, 10 amostras. Entre elas, estamos a falar de escala 1 por 100 mil, a uma distância aproximada de 15, 12, 14 quilômetros. E as análises laboratoriais deste lado deverão ter coincidência com as análises laboratoriais deste lado. Os resultados serão muito próximos uns dos outros. Os resultados deverão ser um dos outros. Ou seja, vamos automaticamente atribuir nomes A e aqui nome B, nome A no caso, nome B, nome C, nome D, e assim vamos pintar o nosso mapa de solos, o nosso mapa geológico ou outro. Finalizamos aqui com todo aquele exercício, obtendo uma carta de solos com vários nomes. Por que aqui já não demos códigos e atribuímos nomes? Porque já fomos a campo, já recolhemos a amostra e já validamos as amostras em laboratório. A diferença está exatamente aí. Essas cores, esses contactos deste mapa de solo é que nos permitem depois começar a caracterizar, por causa destas condições que eles apresentam, qual é o melhor sítio para plantar isto, aquilo ou o outro. Os colegas, se lerem um pouco mais disto, se falarem com a doutora Matoso, a doutora deve vos facilitar aí alguma bibliografia. Nós temos, inclusive, para além deste mapa de solos de Angola, um mapa que nós chamamos de mapa de zonamento agrário. Ou seja, um mapa que tem essas divisões, mas onde cada cor indica o local para se cultivar o produto A, B, C ou D. Os locais para produzir arroz em Angola estão discriminados. Os locais para produzir batata estão discriminados. Para produzir, nós não vamos tirar coisas que se produzem aqui neste tipo de solo para colocar neste tipo de solo. Está provado, está estudado, isso está muito mais do que publicado. Ou seja, era ótimo pesquisar-se um pouco mais sobre isso para falarmos. Como fizemos o mapa hidrogeológico, e aqui já não estamos a falar de solo, já estamos a falar de água. Aqui caracterizamos os tipos de solos que recebem mais ou menos água. Aqui trazemos as formações geológicas típicas nas áreas que cobrem o território nacional, zonas intergranulares, zonas de baixa permeabilidade, zonas cáusticas, e vamos olhar para elas como sendo ali onde existe maior probabilidade de se cultivar e existe menor probabilidade de se cultivar. As zonas de baixa permeabilidade são estas, estão em castanho, e podemos tirar as nossas próprias ilustrações, porque nós todos sabemos o que é um terreno permeável e o que é um terreno impermeável. Se ele tem baixa permeabilidade, quer dizer que ele enxerga pouca água. Se enxerga pouca água, água é igual à vida, e sem vida não há água. Onde não é permeável, dificilmente consegues atingir. Se olharmos para isto, começamos a perceber melhor quais são as zonas que podemos ter agricultura sustentável ou não. Aqui é a combinação do passado, e este tipo de aquíferos, aqueles que nós temos, também apresentam-se, os fissurados apresentam-se mais na zona montanhosa. Se nós formos a Lubango, furamos rochas, e se formos, por exemplo, ao Cunene, já furamos areias. Produtividade, onde é que se produz mais e menos aquíferos, está aqui. E se olharmos para esta área, compreendemos bem porque é que o nosso Cunene tem os problemas que tem. Tacitamente isto. Exemplo concreto, exemplo prático que nós trazemos é basicamente aquele que dissemos logo no início. Por que é que eu gosto disto, colegas? Porque nós vamos ao Cunene. Nós vamos ao Cunene, e eu acho que nos últimos 5, 6 anos nós devemos ter ido ao Cunene mais do que 15 vezes. E nós percorremos o Cunene de les a les. E era ótimo que nós tivéssemos algum exercício prático para percebermos o que é a seca. Nós ouvimos falar, vemos na televisão, mas é uma peça. Tem que ir lá. O que é uma chimpaca? Tem que se compreender isso. Tem que ir para a chimpaca, em extrema época seca, e encontrar um espaço como esse, parece uma piscina do Alvalade, onde num canto estão as senhoras a lavarem, 5 metros depois estão os cabritos a beberem água, 5 metros depois estão os bois a beberem água, 5 metros depois está a população a cartar água, 10 metros depois está a juventude a tomar banho. Tudo na mesma piscina do Alvalade. E saem dali com o copo para a boca. E têm o corpo preparado para aquilo. Os colegas prometem a beber aquela água que ele está a beber, e já vai ver o que é que vai acontecer quando chegar ao teu quarto no hotel. Já vai ver onde é que vai ficar desde 2 até a meia-noite, até as 5 da manhã. Não vai sair daquele sítio onde nós sabemos que me quero referir. Mas como estou numa conferência, não posso mencionar coisas que acontecem em coisas. Mas é exatamente aquilo que iria acontecer se nós provássemos aquela água. Então a seca é mesmo um problema. E a seca agudiza-se aqui, porque estamos a falar do deserto do Kalahari, e estamos a falar da maior concentração de areias que temos nos países da SADC. Estamos a falar de uma zona, um depocentro, onde a profundidade das areias atinge quase os 800 metros, onde, para se ter água, tem que se cavar cerca de 120, 130 metros de mínimo. Então há necessidade de se estudar e se compreender melhor isto, porque se nós não compreendemos isto, não vamos conseguir resolver o problema dos nossos irmãos que estão, sobretudo, na zona sudoeste de Angola. Enquanto que os colegas que estão na parte norte da Namíbia têm estudos mais avançados, porque nos últimos 30 anos trabalharam muito nisto, na investigação, e a crise que nós temos aqui, eles deste lado já conhecem melhor o espaço que têm, já chegam mais facilmente às águas que têm disponibilizadas. E toda esta água que está aqui tem origem na parte central da Angola, que são as zonas de abastecimento de água para os aquíferos da zona sul. Então, isso é um enquadramento, isso é uma tese, está publicada. do norueguês, e estas imagens, este de por centro, foi muito bem desenhado neste trabalho com levantamentos geofísicos que foram realizados. Este é o modelo do aquífero, e aqui começamos a falar de água subterrânea já. Aqui estamos a falar de Angola, e aqui estamos a falar da Namíbia. Isto é o que se deduz ser aquela parte do modelo que antecipa o comportamento do aquífero na Namíbia. Na Namíbia foram encontrados este que é o que nós exploramos deste lado, que são aqueles aquíferos que têm águas reticulares, água da chuva, que se acumulam e que deixam facilmente de existir. Por isso é que nós aqui, quando cavamos, atingimos a água e vai-se buscar 60 a 70 metros, e depois de 2, 4 meses, nós já não temos água naquele furo. É exatamente por isso. Nós não furamos aquífero. O aquífero, na realidade, é este e o outro é este. Eles estão entre eles existem aqui tardos, e os aquíferos que nós exploramos, teoricamente, é este que os namibianos chamaram de KOH0, que têm lentículas d'água, que é este. Por isso é que nós furamos e ficamos aqui 3, 4, 5 meses com água e depois seca. O aquífero que nós devemos explorar, o KOH1 e o KOH0, o KOH2. Este está entre os 120 e os 180 metros, e este está entre os 230 e os 350 metros. Esta água é primitiva, como nós chamamos em geologia, é água que nunca ninguém tocou, é água que nunca ninguém explorou. Os namibianos começam a compreender melhor isto, e em vez de dependerem deste nível de água, já dependem claramente deste e estão a começar a explorar este, enquanto nós temos que perceber como é que isso tudo funciona desde a zona central do país, onde eles recebem a recarga. Ou seja, temos mesmo muito trabalho para fazer. Nós falamos da agricultura, falamos de muita coisa boa, mas nós temos problemas de base que temos que resolver para depois começar a pensar noutras coisas. E é exatamente isso que aqui está. O modelo é namibiano. Nós agora estamos a tentar integrar dados levantados aqui para casarmos e vermos se na realidade isto funciona como se apresenta. E o que é que nós fizemos? Primeiro, fizemos uma pesquisa de todas as sondagens que foram feitas a nível do país. Isto aqui é sondagem dos últimos 50 anos, para interpretarmos cada um dos dados dessa sondagem e começamos então a tentar nivelar ou modelar ou validar o modelo que nos foi apresentado pela Namíbia. Fizemos esse trabalho. Esta carta geológica contempla 3 cartas a escala 1 por 250 mil. Nela foram feitos trabalhos durante cerca de 16, 17 meses, e alguns dados do projeto estão aqui lançados, e como disse, se nós formos ali ao nosso código QR, nós vamos encontrar mais informação sobre isto. Isso é um pouco de todo o levantamento geofísico que se fez. Preveu-se fazer 48 dias e fizeram-se o trabalho em 38 dias, porque houve zonas que não foi possível fazer os levantamentos, porque infelizmente, como se a seca não bastasse, também ainda temos regiões altamente minadas nesta zona. E as minas, com os nossos trabalhos de campo, não casam. Onde há minas, a malta nem entra, nem se aconselha. E é a mensagem que se passa. Por isso é que nós, quando vamos ao campo, a primeira coisa que nós fizemos é dizer bom dia, boa noite, boa tarde ao SOBA, né? Porque o SOBA é que vai nos dizer onde é que as coisas estão, onde é que não estão. Não vamos chegar ao campo e nos pôr lá a andar como se estivéssemos no nosso quintal aqui em Luanda. Isso não funciona assim. Então, não fizemos esse trabalho em várias zonas porque não tínhamos condições de segurança. Isto começaram a ser os resultados dos vários loops que se fizeram. Fizemos 112 e quando nós olhamos para a geofísica, ela nos mostra bem onde é que a água neste ponto se encontra, onde é que a água no ponto a seguir se encontra, e o conjunto destes levantamentos foram depois integrados numa coluna e fizemos então aquilo que nós chamamos de correlação. E começamos a ver onde é que temos zonas não aconselháveis para se furar e onde é que temos zonas que realmente interessa furar. Estes levantamentos são resistividade, são levantamentos geoelétricos, e nós sabemos, olhando para aqui, quando a resistividade é alta, a relação água e a corrente é elevada. Quando a resistividade é baixa, da mesma forma. E assim fica mais fácil nós integrarmos toda a matéria estatística para começarmos então a definir onde fazer os furos. Aqui só um ATT, até para os nossos presidentes e vice-presidentes da escola, no CUNEN e dados apresentados pelo governo provincial, na voz da governadora, um furo d'água fica à volta. Está bem, em português demora mais, mas vamos lá chegar. Um furo d'água demora a volta custa a volta de 15 milhões de kwanzas. Nos últimos 5, 6 anos, o CUNEN fez cerca de 580 furos. Tiveram êxito num total aproximado de 10% dos furos feitos. Se multiplicarmos 500 e poucos vezes 15 milhões de kwanzas e de aí tirarmos só 10% de investimento bem feito, damos conta que estamos a lançar muito dinheiro para fora. Ou seja, o diamante, o petróleo do CUNEN, o investimento do governo no CUNEN é nas águas subterrâneas. Eles gastam milhões de kwanzas nas águas subterrâneas. O meu colega no gozo ainda diz, se o que exonera o vice-governador em Luanda para a área de infraestrutura é o lixo, o que exonera o vice-governador para a área de infraestrutura no CUNEN é água. Duas questões, nada a ver uma com a outra, mas é exatamente assim como eles se aplicam no terreno. E fizemos esse trabalho, fizemos um levantamento linear, fizemos outra linha aqui, fizemos a outra, fizemos esta, fizemos na realidade 6 linhas. E cada uma delas deu-nos o comportamento dos locais onde podemos furar. E todas essas áreas são áreas ótimas, com profundidades aconselháveis e profundidades não aconselháveis. O que é que isso resultou no final? Um modelo tridimensional da zona de estudo. Ou seja, hoje o CUNEN nós o temos modelado assim. Se colocarmos aqui uma camada por cima, será a superfície onde estão as casas, onde estão as aldeias, onde estão os municípios. E sabemos claramente onde chegar e furar, onde atingir a água, onde não atingir a água, e o investimento é feito com base em dados científicos. E é isto que se trata de transmitir a quem decide, para que os milhões que se gastam a se fazerem furos para chegar aos níveis de água não podem ser no escuro, têm que ser baseados em conhecimento científico. E o Instituto está aqui para isso, por isso é que nós temos aqui o curso de Geofísica, para dar resposta a essas questões. O que é que podemos dizer mais? As fases que durou o processo, um pouco do fluxograma, não temos aqui muito mais para dizer, um pouco da ilustração do que foi feito, as sondas a furarem, as amostras por metro, atingimos o furo, fizemos 5 furos, o furo mais profundo foi de 405 metros, está-se a estudar agora a esse furo a probabilidade dele apresentar gás ou não, porque na Namíbia, com essa profundidade, chegaram ao gás e estamos a passar esta mesma informação para os nossos colegas da NGP para continuarem a fazer o estudo na direção que lhes convém. Ou seja, aqui nós fomos para a água subterrânea, mas eles vão direcionados à pesquisa de gás. O que vem depois é um pouco do resultado do furo, todos os logs que nós estamos habituados a ver, a posição dos furos no local, como é que está toda essa informação hoje armazenada, guardada, ela tem que estar disponível, como é que ele se fundamenta, e este visor que é aquela área onde nós temos a possibilidade de qualquer um de nós chegar e visualizar e ter acesso às coisas como são. Aqui não se faz download, aqui se observam as coisas e facilmente se chega lá. Nós já passamos a fase de andamos a decorar links, né? Agora está na moda usarmos os códigos QR, porque os telefones vêm preparados para isso. E é com essa direção que nós tentamos colocar tudo o que se fez à disponibilidade tanto de estudantes, tanto de investigadores e não só. Mais informações, mais dados. Os colegas são convidados a visitar o Instituto Geológico. Aconselho a visitarem, porque para além disso tem laboratórios, tem muita informação que pode ajudar nos trabalhos finais, nos TCCs e se calhar facilitar um pouco a vida de todos que por aqui passam e aqui estão. Passem a mensagem aos outros colegas, nós continuamos deste lado, a direção tem um memorando conosco, facilmente os colegas conseguem fazer estágios, temos estado a fazer muitos estágios com estudantes de SPTEC, de 3, 2, 1 mês, e pensamos continuar porque, vice-presidente, é a nossa obrigação. Sua Excelência, muito obrigado, mas o português é mesmo assim.
Thank you, Professor Americo. Okay, don't go because we have a lunch and we're not going to take any question right now because we are working with time. Just to announce you that Dr. Marcel is one of the co-hosts and we have another hostess abroad. And we are working, they are connected with us. This is the time for lunch to them. And we took them 7 minutes, which is not fair. When we will come after lunch, if you have a question, we're going to open maybe 5 to 10 minutes to ask a question to Dr. Americo, but not now. And during the lunch, you can sit close to him. If you have a question, ask. Once again, Professor Americo, well done. This matter is a big problem for public health in our country. Enjoy your lunch. Okay, our lunch is in protocol. Can you help us? O lanche é onde? Onde tivemos? Okay. We can take our way to the lunch. It's not a breakfast, but it's proper lunch.
while driving in the backseat. What's left of me? Drowning in my fears is like an ocean. Negativity is getting closer. How to keep the heat when it gets colder, you know. Sometimes everything just gets hard. Sometimes everything just gets harder. Feeling like I'm missing some parts. Days just keep on getting much darker. Even when I'm down in the lower, I remember what you were saying. Sometimes all you need is a spark. Maybe just a better kind of bitter. Lose gravity, I'm swimming in the quicksand. Up to my knees. Keep losing sleep, I'm addict dream at midnight. So hard to please. Drowning in my fears is like an ocean. Negativity is getting closer. How to keep the heat when it gets colder, you know. Sometimes everything just gets hard. Sometimes everything just gets harder. Feeling like I'm missing some parts. Days just keep on getting much darker. Even when I'm down in the lower, I remember what you were saying. Sometimes all you need is a spark. Maybe just a better kind of bitter. Think about the stuff we play. How I'd rather do that instead. I keep screaming out loud from the top of my lungs, baby. Ooh, think about the stuff we play. How I'd rather do that instead. I keep screaming out loud from the top of my lungs, baby. Ooh, think about the stuff we play. How I'd rather do that instead. I keep screaming out loud from the top of my lungs, baby. Ooh, think about the stuff we play. How I'd rather do that instead. I keep screaming out loud from the top of my lungs, baby. I've been thinking about you. I'm waiting for it all to come true. I'm longing to hear you say, you know that I miss us. I wanna be the one that you trust, 'cause you have stolen my heart away. There can be no other. Baby, I don't even bother. Whatever they have to so come and take my breath away. Come and take my breath away. Come and take my breath away. It's getting harder. I'm begging you to choose me. I never thought I'd feel this way. Never thought I'd feel this way. Every day it's getting harder. Begging you to choose me, so come and take my breath away. Come and take my breath away. Every day it's getting harder. Begging you to choose me. I never thought I'd feel this way. Never thought I'd feel this way. Feel this way. I can hear them thinking out loud, loud. Simple people acting so proud, proud. I hear them talking, talking, talking about us. Yeah, yeah, yeah. I can hear them thinking out loud. One might think it's obvious. Please don't spill your mind when you don't have a clue. Hey, they don't know about us, babe. They don't know about us. They can think what they want, baby, but they don't know one thing. Even if they did have a glimpse of our truth, they wouldn't know about us. No, they wouldn't know about us. They keep wishing that I'd fall in line, line. But you and me, babe, we're one of a kind, kind. One might think it's obvious. Please don't spill your mind when you don't have a clue. Hey, they don't know about us, babe. They don't know about us. They can think what they want, baby, but they don't know one thing. Even if they did have a glimpse of our truth, they wouldn't know about us. No, they wouldn't know about us. They don't know about They don't get it, babe, living in a cruel world. It's a rare thing to do just what we do, love. Hold your head high and do it by your own terms. They don't get it, babe, no, they don't get it, babe. They don't know about us, babe. They don't know about us. They can think what they want, baby, but they don't know one thing. Even if they did have a glimpse of our truth, they wouldn't know about us. No, they wouldn't know about us. They don't know about
I was living in the clouds, yeah, like a million explosions. Whatever happened to the picture? The one where you and I were perfect. Like if heaven was a time lapse. Play the story where we'd end up. Would you pause it for a second before this thing's over? Would you come a little closer? before this thing is over. Won't you come a little closer? Man up till it's gone, 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 it's gone, it's gone, it's gone, man up till 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 it's gone, it's gone, it's gone, it's gone. When the light begins to darkness and your fears all turn to regrets, how do you stand up without falling? How do you see it as a blessing? As I'm falling through the water, let the ocean be my witness. I believe that this has changed me. I pray it as I'm sinking. This time will be different. Pray it as I'm sinking. Man up till it's gone, 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 it's gone, it's gone, it's gone, man up till 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 it's gone, it's gone, it's gone, it's gone, man up till 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 it's gone, it's gone, it's gone, it's gone, man up till 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 it's gone, it's gone, it's gone, it's gone. I'll be missing you, love. Yeah, I'll be missing you, love. And the good times that we had, I'll be missing you, love. I'll be missing you and your love, your love, your love. When I think of you and the two of us together, felt so good for so long. It was you and me forever. Now you walk away, maybe for the better. So tell me something true. Will you miss my love? I'm still missing love. All the good times that we had, I'm still missing your love. I'm still missing you and your love, your love, your love. Oh, baby, I'm still missing you. Still missing you, missing
If you're thinking about leaving, let me know. If you're thinking that you don't wanna hurt me, going, I'm getting bored. 'Cause I can find another, so don't hold me back. You're not allowed to spend my time, 'cause that is what you came here for. Oh, this is what we gonna do. You never come clean and you never come through. Take your shit and don't come back. Looking so surprised how you could do me like that. You think it was all up to you. Give me some space, I don't care what you do. And give me back my money too. 'Cause I'm going out tonight. I'm gonna leave it all, yeah. I won't let him get into my mind, no. Oh, he thinks he can, 'cause he's a man, but he is just a boy, no. Won't let it steal away my shine, no. I know you're thinking about me from time to time. Before you do anything stupid, think before you speak your mind. 'Cause I am on a roll, yeah. So don't hold me back. You're not allowed to spend my time, 'cause that is what you came here for, right? Oh, yeah. This is what we gonna do. Oh, you never come clean and you never come through. Take your shit and don't come back. Oh, you're looking so surprised how you could do me like that. You think it was all up to you. Oh, give me some space, I don't care what you do. And give me back my money too. 'Cause I'm going out tonight. Leave it all behind. I'm gonna leave it all behind. I won't let him get into my mind, no. He thinks he can. He's your man. He's just a boy. Oh, won't let it steal away my shine now. Get up and try again. Oh, I won't let him get into my mind now. Oh, he thinks he can, 'cause he's a man, but he is just a boy. Won't let it steal away my shine now. Get up and try again. I get up and try. Get up and try again. Get up and try. Get up and try again.
I remember getting locked up in myself. That thing of loving was for everybody else.
been hurt too many times. Gave up on hoping, thought I'd never get it right. It's all because of you. It's all because I have to tell you, baby, there's nothing more I need but you. It's you. There is no greater meaning. Nobody does the things you do. It's true. How we get lost in each other. Everything blurs when I'm with you. Us two. I wanna stay forever, safe in your arms. I know that baby, you do me right. Boy, you bring me something that I never knew. A kind of happy I don't ever wanna lose. And when I hear you coming knocking on my door, all I think is, baby, I need more. I need more. It's all because of you. It's all because I have to tell you, baby, there's nothing more I need but you. It's you. There is no greater meaning. Nobody does the things you do. It's true. How we get lost in each other. Everything blurs when I'm with you. Us two. I wanna stay forever, safe in your arms. I know that, babe, you do me right. There is no one better. I take on the world with you. With you. I've had many lovers, but no one comes close to you. To you.
Recording in progress.
We paint different colors too. We do. There is no one better. I take on your look like very good. Let me tell you, I have to tell you, baby, there's nothing more I need but you. Nothing more I need. It's you. There is no greater meaning. Nobody does the things you do. Those things you do. It's true. How we get lost in each
Recording
other.
stopped.
Everything blurs when I'm with you. Us two. Let me stay. I wanna stay forever, safe in your arms. I know that, babe, you do me right.
I've been missing the way you touch me, baby. Kisses on my neck and the love you gave me. When I think about it, I go a little bit crazy. It's gotta be more than this for you and I to coexist. Help me, I wanna be more than just a friend. I'm looking for closure, so baby, pull me closer. Help me, I don't wanna be just the one
pull me closer. I've been scrolling through the text messages you sent me, trying to fill the holes where you left me empty. And when I think about it, get a little emotional, knowing that we might never ever be close to loving. Help me, I wanna be more than just a friend. I'm looking for closure, so baby pull me closer. Help me, I don't wanna be just a one night stand. I'm looking for closure, so baby pull me closer. Help me, I wanna be more than just a friend. I'm looking for closure, so baby pull me closer. Help me, I don't wanna be just a one night stand. I'm looking for closure, so baby pull me closer. Sober up, think it's time for me to sober up, 'cause I don't know what I should do with all these feelings. Don't wanna be needy, too in love. Maybe I am just too in love. Baby, all I know is I can make you stay, but don't just walk away. Help me, I wanna be more than just a friend. I'm looking for closure, so baby pull me
Recording in progress.
Help me, I don't wanna be just a one night stand. I'm looking for closure, so baby pull me closer.
Oh, we're living in the present, but our mind is in the past. Not knowing what we lose, don't know what will last. Yeah, the things you always dare to dream. Oh, are not always what they seem. Close to total peace as the pain begins to ease. Not often we can see the beauty in the pain. Not often we can see the value that we gain.
Good afternoon again. How was the lunch? Did you enjoy it? Great. I hope so you reserved some space where you're gonna eat again the coffee break. But I will advise you also to reserve another space where you're gonna put the food from home. Otherwise, from here, you go straight to sleep, which is not good. You need to eat the food of your wife or the food of your husband. Okay. We are continuing with our conference or our workshop. Once again, I would like to thank Dr. Masilu bringing this great vision among of academia. There is no science without of workshops, without of conference. This is what makes us to be what we are. And also, if you are a professor, you are a student, without of participating to this kind of activity, you're not going to increase your vision. Different topics that we are listening, different point of view is building our career. This is something very important. Like as in the UK, to participate in activity like that, you're not going to pay less than 200 or 300. We have here engineering. Adilson can testify that. To participate this kind of activity, at least for 3 hours, you can pay 300 or 400 pounds. But here is free. Some people, they prefer to sit down in the office or even going around. But you are lucky because you choose to be here. I would like to ask Dr. Thomas King. I don't know, Professor Cirillo, if everything is okay. Dr. Thomas King is an early career researcher fellow at the University of Birmingham in UK. He holds the undergraduate degree and also have a postgraduate degree in geology and geophysics from the University of Aberdeen in the UK, and is a PhD in rock mechanic from the University of Torino, Italian. That means Dr. Thomas, he have the background from the Birmingham University, background from Aberdeen University, and also the Italian University. His research focused on the practical application of novel science methodology at the interface of the nature and built environment. Thomas has worked on the deployment of quant sensor in field of environment and has developed a new analysis strategy to monitor geologically feature at multi-scale. Is someone well qualified to speak among of us? If Reggie, are you ready? Please help me to introduce Dr. Thomas King. Dr. Thomas King, you are welcome. We believe that you are far away, but next time we're going to be together in Angola. Please, we can put our hand together to welcome Dr. Thomas King. The word is yours, Doctor.
Thank you very much. Thank you very much for the invitation to be here today. It's a great honour to be a part of this. Today, I'm going to talk about some large-scale laboratory-controlled testing that we have been conducting at the University of Birmingham. And the purpose of this is to test geophysical methods and find out their strengths in detecting water resources. Today, I'm going to talk about how we're using a parameter known as microgravity to find resources under the ground. By using these remote sensing techniques, you don't need to dig any holes, you don't, such as excavation, you don't need to find the water physically. We can detect it from the surface itself. As a brief overview, I'm going to go over kind of what is the main challenges that we're trying to address, what microgravity is as a parameter, and what is it sensitive to. I'm going to go over the general aim of this study and some of the experiments that we've been conducting help bring us a bit closer to solving these challenges that I'm going to go over, and going to show some results as well. So as this whole workshop is highlighting, groundwater is a major issue. One of the key challenges is in excess removal of water, and this can lead to challenges in, say, aquifer depletion. That can also lead on to issues such as land subsidence, a reduction in the water quality due to an relative increase in the number of pollutants. And this goes on to have quite significant impact on the local ecosystems. Indeed, a recent UN study estimated that the global cost to manage irrigation and water around the world will amount to about $1 trillion by 2050. Therefore, being able to map the soil and the moisture condition would provide the necessary insight to kind of better manage our water resources and better manage our agricultural regions. So in terms of where microgravity fits in as a geophysical parameter, on the left-hand side, you see this very simple figure where we have the size of the feature that we might be interested in and the depth at which it is. So, for example, methods like electrical resistivity, they're very sensitive to very shallow, very large features, whilst methods like ground-penetrating radar are much more sensitive to kind of smaller features that are very much deeper. Microgravity and gravity sensing methods kind of sit in the middle in terms of their sensitivity. As shown before with the satellite work colleagues have been conducting, gravity is sensitive to variations in the density of the subsurface. So where we find materials of high density, we get higher gravity. It's a nice one-to-one correlation. However, in the context of water resources, water increases the local density. So if you find a dry area and then you find there of increased density underground, we can potentially say there is water there. One of the advantages of this method is that it's recording the natural passive field of the Earth. There is no signal to attenuate, and this reduces one of the key challenges with, say, GPR and electrical resistivity. They can't work in all environments. But because of this sensitivity to the natural Earth, it's also very sensitive to ground vibrations. As an example, a single measurement can take typically between 30 seconds and 2 minutes to complete. If a van drives past the instrument, or even if your colleague walks too close to it whilst measuring, the data point is ruined. And it means you need to redo the measurement. And this can be very, very time consuming. And this further limits where we can actually use these methods. One of the things, though, that we are developing at the University of Birmingham are quantum sensors. These are sensors that rely on the repeatability of atoms. And one of the key findings those developers are finding is that it's much less sensitive to noise sources. And in this case, it means it can be applied to find much smaller signals and much greater depths that current sensors can't actually allow currently. So, as I said, at Birmingham, we have been developing a quantum gravitometer. This is the large blue tube on the left. And we've been deploying it in a number of field environments in order to help understand how the sensor is working, what features it's actually sensitive to, and ways we can improve this. The current improvement. And when we were looking for these very, very sort of small water feature signals in the field, it gives us there's significant potential for better management of them. As part of our continuing work in Birmingham as well, we are planning to take the quantum sensor out into a real-world aquifer up in the north of England, and we'll be using it, and we'll be working closely with BGS to map and monitor those resources to demonstrate the benefits that quantum can bring to kind of these agricultural regions. And this will also be further complemented by additional monitoring, additional kind of detection tests in the laboratory, so that we can be much more confident in our observations and ensure that the sensor is working as we hoped. Yes, thank you very, very much for listening to me. If anybody's interested in seeing NBIF more as a facility, it really is a state-of-the-art laboratory. Please visit our website. And I'd like to ask for any questions.
Thank you very much, Mr. Thomas. We are so happy for your presentation. I don't know if someone have a question. We're going to collect even 2-3 questions. Okay. Microphone protocol, please. Protocol. I do have also a question, but as a moderator, I have to wait for you to ask first.
I ask in Portuguese.
Okay, you can introduce yourself, please, before.
Arturo Miguel, teacher of SDG.
Okay, thank you.
Yeah. I want to ask, it's possible. Oh, em português.
Só que ele não vai entender.
You translate.
Yeah.
Eu queria perguntar se é possível a aplicação.
I would like to ask if is it possible the application.
A aplicação desta mesma técnica não só para a busca de água, senão em aplicação em outros campos, como o caso, por exemplo, de metais ou outros minerais que não são metálicos, se é possível aplicar a técnica de quantum sensor para, sobretudo, na prospecção deste tipo de materiais.
Dr. Thomas, my question is, I want to find out, it is possible to apply the same techniques, not just to collect water, but for different fields?
Oh, of course, absolutely. So it's not so much water. One of the key interests in Birmingham is for management of civil infrastructure. So in our cities, we have a lot of old pipes, old tunnels that aren't properly mapped. In addition, we have old mining areas where the mines aren't actually properly marked on our maps anymore. We need to be able to find out where they are before somebody, say, falls into them and gets hurt.
Okay. Prof. Arturo, I think you got the answer. It's better to use microphone. Prof, é melhor mesmo falar mesmo em inglês como estás a falar, ele vai entender. Assim a discussão vai fluir bem.
Não, porque o que eu percebi é que não terminaste a pergunta. Se você perguntar se pode ser aplicado em outros campos, ele logicamente vai te responder que sim. A minha pergunta é específica, sobretudo na área da mineração, da detecção de metais, ouro no caso, ou de outros tipos de minerais.
Okay. I think the way that I asked the question, it was too broad. Going specific, like it's possible to use it to the minerals. Like in Angola, we have diamond, gold, metals, specific like in metals.
Specifically, it would probably be very challenging because over such a broad distance where these minerals may be located, it may be hard to distinguish them because the signal differences would be very, very small. But yes, if quantum does show this increase in sensitivity, we could potentially detect, say, more dense minerals such as lead from a less dense material such as aluminium.
Okay, now adding my question on the top of Professor Altug, have you done it or do you have similar research but specifically to the gold or metals?
No, not personally, no. My background is in monitoring volcanoes.
Okay,
So
Prof. Altug,
so
this is a great
macro
opportunity
resources.
for you. Maybe you can design any proposal to work together with Mr. Thomas.
That would be very interesting.
Thank you. If the professor is not going to do it, maybe I'll try to create my proposal, and I believe we can get funding from Birmingham. Some grant?
Yes, we should try.
Okay. In 2 weeks' time, by Dr. Marcel's permission, I will contact you.
Excellent.
Okay. Thank you very much. More question? Another question?
Hello, right. My question is regarding the quantum sensor. So the first question that Herr England guy asked to do is the price.
The price?
Exactly.
So the sensor we have has been in development for about 10 years, and I've been told it's worth about £1 million.
All right. Imagine that we have this equipment in our lands. So how long time is necessary to get the results?
So, as I said, a single measurement can take about 2 minutes with conventional devices. So those maps I produced where I took 50 measurements, that took several days to conduct those studies.
All right. So what is the big difference between the quantum sensor and another methodology that you read there?
How they take the measurement. With a classical instrument, you have a test mass on a spring. And as you go over more dense materials, the test mass is attracted closer to that material, so the spring lengthens. This is, of course, because it can vibrate as well, it's very sensitive to ground interference. With quantum sensors, we are using a cloud of atoms as our test mass and a laser as our spring. And this is much less sensitive to those vibrations from the ground and is also much more repeatable. So, for example, we are using atoms of rubidium in our sensor, and an atom of rubidium will always be an atom of rubidium no matter where it is. And this kind of helps deal with this noise issue.
Very, very good. What is the maximum large area that he can cover?
Pardon?
At the maximum large area that this equipment can cover. The area is
the changes in mass.
What is the maximum area that the equipment can cover?
Oh, depends how far you're willing to push it.
Exactly, the far away.
It's currently quite large. So one of the teams in Birmingham are working on miniaturizing it. So the commercial devices are, say, about this big. This is very easy to carry. They only weigh a couple of kilos, and we can move it around. The new quantum sensors that are in development aim to get to those sizes as well, and so they still can be more portable and actually usable.
Sorry to cut you, because I'm talking about the land. I'm not talking about exactly the equipment. I'm talking about when we use the equipment to measure some lands, how can the equipment can cover the area? I'm talking about the area that equipment can cover.
In terms of a parameter, gravity is sensitive to everything between yourself on the surface and the center of the Earth. In terms of sensitivities, we are sensitive to the orbit of Jupiter. These are the kinds of signals you can track with gravity. It picks up everything.
Okay, thank you very much for great discussion. My question has been asked. You asked my question, what I wanted to ask him about how he analyzed all the data, but I got the answer. Please, we can put our hand together to appreciate the work that Dr. Thoms has made. Thank you very much. We hope that next time we're going to see you in Talatona in Luanda. Great. Okay. We are moving on to another presentation. I would like to introduce Professor Dominique. Not Domingos. I'm Domingos Vita, but now we are getting Dominique. He's a postdoctor researcher from University of Strathclyde, UOS, with expertise in development of optical is after Mark. Okay, sorry. I can't get the program that you sent to me, Prof. I'm so sorry. As you know that human being, you can make some mistake. Can you apologize me? Oh, nunca je me perdoa. I was calling the wrong speaker. Now we go to Dr. Mark Bassoni. Is any experimental quantum physics, STFSC, Real Space, the UK National Lab for Space Science, is a researcher experienced in quantum technology, include magnetometric, laser calling, atom interferometric, and Rydberg physics. He was a Mary Core Fellow at Aalto University in Denmark, and he has postdoctoral experience from the University of Pisa in Italy. He was a researcher, investigator on the second phase of UK National Quantum Technology in sensing and timing, in which he developed a range of optically pumped magnetometers. Yeah. Ladies and gentlemen, please help me to host in this afternoon, in this workshop, Dr. Mark Bassoni, by putting our hands together. Dr. Mark, we are clapping for you. That means we are happy to receive whoever that you'd like to talk to us. We are ready to receive it. Feel free to speak to us. The time is yours.
Mark, is everything all right with your sharing? Because I can't see anything on the screen.
Can you hear me, John?
Yeah, I can hear you.
No, I'm sorry, my computer is completely frozen. Maybe is it working now? Sorry.
Oh, yes, it is now. Yes.
I'm sorry about that. I started sharing my slides and everything collapsed.
Okay.
I think my computer knows it's Friday afternoon.
Yeah,
Can everybody hear me in the auditorium? I can't hear anyone. Should I carry on?
I think I would. Yes, it's fine. I can hear it.
Okay,
It's
perfect.
from people.
Okay, thanks for the invitation, everyone. Sorry I can't be there in person. It's been a very enjoyable workshop. So hopefully this will continue into the future. So I'm Mark Basin. I'm from RAL Space in the UK. And so I've got a little bit about quantum mechanics coming up later, and what quantum sensing is. But in terms of an outline, I thought I'd tell you who we are, so you know where we're coming from, why some people are suggesting quantum sensing from space is a good idea, and then some of the ways in which we're trying to make that a reality. So we have a picture here of a vacuum system here, which holds atoms which are very close to absolute zero. And then I'm going to start at the end of my talk, start at the beginning of the talk with the messages I'd like you to take away at the end of the talk. And the first one is that quantum sensors are just sensors. So we judge how well our quantum sensors work compared to classical ones. And even though we use the magic of quantum physics, the end result is useful. And we're going to look at sensing gravity from space. And so improvements that we get in our classical quantum sensors should give an improvement in spatial resolution. So this is related to Professor McDonald's talk earlier.
Mark,
and then another.
Mark,
Yep.
I'm sorry to interrupt you, but I think we can only see your first slide.
Okay, I will resume
You
sharing,
just
maybe.
shared your screen. Maybe you just shared your screen rather than, yeah, there you go. It's on the key messages now.
Okay, yeah, this Zoom is not playing well with me, but you can see the key messages, yeah? Okay,
Yeah.
sorry, that's kind of. And then we'll talk a little bit about how combining some of the expertise can hopefully get these sensors into space. Can you see the next slide now, who we are?
No.
No.
Key messages.
I'm going to stop sharing and share again, I think, because it's not behaving very well. There. Maybe. Is that there?
Yes, so we
Yeah,
have
okay.
government and
Yeah. Yeah, so we're ultimately funded by the government directly through one of the government departments. So REL Space is part of UK Research and Innovation, and in particular part of one of the funding councils, which is called STFC, Science and Technology Facilities Council. And physically, I am located in the definitely non-tropical area of Oxfordshire at the moment, which, if we're talking about space, is somewhere there in the UK. And yes, we're the National Laboratory for Space, so we've been going for over 60 years, and we have around 350 different employees across different divisions. And we got 2 sites, so in addition to the one in Oxfordshire, we also have a ground station in Chilbolton. And so we do everything we can to help the space industry and to launch missions and build and test spacecraft. So we've got next generation missions coming up, and we span the whole range from Earth observation up to astronomy and very many places in between. So as an example of one of the things we do, we take cameras and we point them at the sun. So this is something that my colleague has helped with. So this is looking at solar activity. So yeah, my colleagues have developed the electronics for this. And this is particularly interesting for things like space weather, where you have explosions from the sun, and these ionized particles make their way to the Earth and disrupt normal life. Okay. So let me move on. So yeah, why would you try and put quantum technology into space, and what could you put into space? So actually, we're going to focus on the first example here, which is acceleration. So gravity is the type of acceleration, but there are a variety of other things that you could measure. So I think Dominic's going to talk about magnetic fields next. You can also measure rotation, and you can put very precise clocks into orbit. And then in addition, people are looking at putting memories. So like you have memory in a computer, you can also store quantum information, and that should be useful in things like telecommunications. So these are all grouped under the fact that they either use quantum superposition and/or entanglement. And I will try to talk a little bit about what quantum superposition is, because that's at the heart of the sensor that we have. But yes, as we've seen before, we're going to be measuring acceleration. And, and if we do that from space, then we're sensitive to all these different types of processes. So I'm not going to go through them now in detail, but obviously we've been talking about groundwater storage so far. So that's indeed one of the things that we're sensitive to. But we also have all these other sort of competing effects. So ice sheets in Greenland is another thing that we could observe. And as Thomas said previously, the classical sensors can be grouped into these sort of different techniques. So he was talking about this spring. So in the bottom left, we have this Syntrax CG5. And these work very well, or reasonably well already, including in satellites, these types of electrostatic sensors. So what do we think we can do better using quantum sensors? This is actually the fairest comparison of a quantum sensor in space, and that's a classical type of sensor in space. So Professor McDonald's talked about these missions, Grace and Gocha, and they measure the gravitation acceleration from low Earth orbit. And with all the measurements, they can put them together, and they can make images like this, which is the Earth geoid, so showing areas with higher gravitational acceleration or higher mass, and how those things change over time. So here we have water movements across the globe, so we can see seasonal trends, as Professor McDonald explained before. We'd obviously like to do better than this, so in particular, improving the resolution. If we want to do that, we should compare ourselves again with Gocha, which has a resolution of about 100 kilometers. And we'd like to push towards this 10-kilometer resolution. And then on the right here, we have a range of different processes that we should then be sensitive to. So we have these 3 different satellite missions, CHAMP, Grace, and Gocha, with the sensitivity on one axis, so that the time on one axis here, so all the way down to annual and seasonal changes, and then the spatial resolution here on the x-axis. So some of these will be familiar to Thomas in the geophysics area, such as the volcanoes you mentioned. And then we're going to try to push down into this hydrology, so looking at groundwater. And so it's this improvement in sensitivity, which we hope will give an improvement in spatial resolution. So now we'll get to a little bit of quantum mechanics. Apologies if I lose anyone here, but I've hopefully started from the basics, which is the periodic table. And so we have something usually taught in high schools or just before university, which is the Bohr model of the atom. So here we have the example of nitrogen. We have the proton and neutrons confined at the center, and we have the electron clouds floating around, and these electrons are in specific orbitals. And then we want to study how light affects these electrons in the different orbitals. And you may be familiar with the idea of quantum jumps. So here I have a little cartoon on the left, which is showing time on the x-axis and energy on the y. And we have an atom which is happily sitting there in its ground state. It's moving along in time, and then it absorbs a photon. This is my little photon here, and it will jump to a higher state, and then it will stay there for some time. Carries on like that. The frequency or the change in energy that you can give to this atom is related to these electron orbitals. So for example, you can be sensitive to light, which is around blue. So this is 486 nanometers, or one's at 656. But if you have light with a color in between, it doesn't really do anything to the atom. We don't move the electrons around. And then if we develop from this idea, this is actually something called a two-level atom. So quantum physicists like to express this in terms of an excited state, so with a higher energy, and then a ground state. And these electrons or atoms can move between these different states by interacting with a laser beam. So we like to confine atoms in little holders. So this may be a vacuum chamber, or maybe a vapor cell, like Dominic will mention next. And then can shine lasers on, and what happens is that the atoms oscillate between these different states. So this is an example of shining on a laser for a different time and looking how the atom oscillates between the two. So here we have it all the way. 0 is meant to be the ground state, and 1 is meant to be the excited state. So if we look somewhere in the middle, we're not in the ground state, and we're not in the excited state. And this hints at something called quantum superposition. So this is one of the fundamental principles of quantum mechanics, and that's a quantum state which can be represented as the sum of two or more states. So this is my cartoon again here. We have a ground state atom, an excited state atom, and they have some kind of superposition, or this is what the dotted arrow represents, and then a cloudiness around it, which represents some kind of probability. So it's a little bit hand-wavy cartoon, but hopefully makes sense. And actually, you can see these things in single atoms. So if you have just a single atom sitting still on its own, so this is actually a strontium atom, and if you measure what happens when you shine the light on for a certain amount of time, you can measure being in up or the down state with different probabilities. So here, for example, I start with it in 0, and I measure it all the time, and I always get 0, as this small error bar suggests. And if I shine on the laser beam for about 40 microseconds, then it will always be in the excited state. So that's great. How can we use this? Well, the first thing we need to do is we need to get this atom to stand still. So in sort of contrast to the atoms in the room around me and the ones around you, which are moving at thermal velocities, so at about 300 Kelvin or something, we need to get them to stand still, or as close to stopped as we can get them. And to do this, we need to cool them down to very low temperatures. So if we compare the image of the sun that we had before, so it's about 6,000 Kelvin, we can cool things down to lower than the cosmic microwave background, which is about 4 Kelvin, and all the way down towards absolute 0. So we can't get exactly to absolute 0, but we can get very, very close. So this is a log scale. So this 1 microkelvin here is 1,000 times warmer than a nanokelvin. And people routinely can get down to a nanokelvin now. So they're moving then at maybe a millimeter per second instead of hundreds of meters per second. We do this in vacuum chambers. So we take out the air, which would otherwise heat things up. And we use a technique called laser cooling to capture these atoms. We'll move on to that now. So we then think about the atom as moving and interacting with a photon from a laser beam. This is, again, my cartoon here. So we have an atom moving towards the right, and we have a laser beam, which is composed of photons moving towards the left. And we fire as many photons as we can at this atom to try and slow it down. So the analogy I like to give is having an elephant charging at you and having some ping pong balls and hoping that you can use those ping pong balls to impart momentum onto the elephant and slow it down. Obviously, you need lots and lots because the photon doesn't carry much momentum. But if you have enough, and then you rely upon this effect that the emission of the photon or the readmission of the photon from the atom is in a random direction. So as you have a preferential absorption direction, the emission is random. And that means that you can get a net transfer of momentum from the laser beam to the atom. So then in the right here, we have an image of rubidium atoms. So we have a cloud of about, do I have the number exactly? Yeah, about 10 to the 9 atoms and about 15 microkelvin. So actually, what's happening here is gravity is in the right, is in the x-axis here, and they're falling under gravity for about 10 milliseconds or something. And we're going to use those atoms falling, and we're going to compare that in our interferometry. Okay, so again, we're going to measure acceleration, and we're going to use a superposition principle in something called atom interferometry. So the sort of light equivalent of this, which we're going to use as an analogy for the atom interferometry, is that you can split light. And so we would have, let's say, one state which would be bounce off this beam splitter, another one which would pass through, and then you can recombine them again. And if you do recombine them, you will get an image a bit like the one below here, which is of dark and bright fringes. This image is then sensitive to the paths that these photons take in the case of light. So if I displace this mirror a little bit, that will then shift these fringes. So if I wanted to measure very accurate length scale, then I could use this effect to measure the position of this mirror. So people who detect gravitational waves do something very similar to this. In the atom case, it's very similar, only we have a different sort of wavelength associated with the atom, which is too much to go into now. But we know that these fringes, or the phase of these fringes, is actually proportional to the gravity. So this is my little g here, and that's something that we want to measure. We have k, which is related to the wavelength of the light, and then we have time. So how long we drop the atoms for dictates what type of phase difference we can measure. So people have been measuring this now for almost 20 years. This is an example, again, like the one we showed you before. And then of the atom that I showed before with the probability of being in different states. And then this is measuring local gravity. So similar to what Thomas and his colleagues will do in Birmingham. This is looking at the tides, so the earth tide and the oceans coming in and out. And then you can compare these to certain models. Now the big jump we want to make is to take these types of sensors, such as the ones that I've developed at Birmingham, and put them into space. If we do that, I'll just draw your attention to this bottom left diagram. So here we compare the sensitivity of the quantum sensor. So this would be this cold atom gravity gradiometer to what the classical versions have, which is Gocha that I've mentioned before. And we can see that we're at least a factor of 5 or something better in sensitivity, depending on which frequency you're interested in. So this is now 1 hertz all the way down to a millihertz. So we believe that the sensitivity is better. And so now we're looking at ways in which we can get these reliable systems into space. So we've been collaborating with our colleagues in Birmingham, as well as Teledyne E2V, and also colleagues in Germany. Hanover in particularly, and with the European Space Agency to develop smaller, lighter, and less power-consuming payloads for missions that we'd like to launch. And so we have the sensitivity, we believe, and then we want to map this into resolution, again, for the arguments that we had before. And so this naturally asks the questions of how do you improve the spatial resolution, say down to this 10-kilometer limit or goal, if your satellites are quite far away from the subject of interest. So they're in Luanda, you would probably want to get the satellite as close as possible, because then you'd be able to pick out these fine features, these high resolution aspects of the water signal, for example. But there's a problem in going close to the Earth, and that's that you start to hit the atmosphere. So you can move closer, you can have an orbit which is low, like the ones of Grace and Gocha, but then the atmospheric effects will slow your satellite down, and then you will eventually tumble back down to Earth. So this is something that's actually not very well understood, and it means that we are interested in measuring the atmospheric drag to inform things like satellite lifetimes, to improve our models of atmospheric science. And so this is another sort of type of application of the quantum sensors in space. So this is called the Casper atmospheric drag mission. And then we have the benefits of included sort of, in addition to the thermosphere understanding, so that's part of the atmosphere, we can also predict the orbits. So if we have an increasing number of satellites in space, the risk of collisions increases. So we need to be able to predict what's up there and where it's going to be in, let's say, a minute or an hour's time. And that's something which we hope these drag measurements will give us some understanding of. Okay, so just lastly, I'll say a little bit, if my slide will move, a little bit about what type, oh no, I've gone too far. What type of techniques, sorry, my computer is really suffering today. What type of techniques we've been developing to do that. So this is just one slide where we have an example of a 3D printed vacuum chamber. So as I said before, we need to keep these atoms away from the thermal background that we have in the office or out in the field. So we pump out all the air, but these things can be quite heavy. So you'd usually make them of stainless steel. And so we're looking at ways that we can use 3D printing of metals to sort of reduce the weight. And so that obviously that's important in getting things into space. Then we're also working on magnetic traps. So this is passing electrical currents through wires and using the magnetic fields that those wires create to make potentials for our atoms to sit in. And so this is a low power version of what people use generally in the lab. And so we've been testing or building, designing and testing these things, so shaking them to qualify them for rocket launch. So that's where we're up to at the moment. As you've seen already, this isn't just my work, it's that of all my colleagues. So in particular, all these fine people are quantum scientists. And then we have support from electrical engineers, such as Adam and Mike, and then Tim Thornton, mechanical engineer. So that's it for me for today. I'll just hopefully get to the summary slide. So yeah, we're looking at sensors based on quantum principles, and we have applications in Earth's observation, also fundamental physics, and we're trying to raise the technology readiness level. Thank you very much.
Thank you very much, Dr. Mark. Okay, going straight away, we are nearly done. As we say in Portuguese, aqui nada vamos terminar. Just 2 more speakers left. There is any question? Let us make our question brief. Professor Teresa, please.
Hello, yes, Dr. Mark. It was a very
Hi.
interesting presentation, but you're going to answer something for someone that doesn't have any experience in quantum physics. So I just wanted to know if you guys have calculated the energy consumption of your equipment.
Yes.
Okay.
Yeah. So we actually, this picture here at the top right has a little, let's say, hint at what energy we're expecting to consume. So we're limited by what solar power we can get. So the solar panels here are covering the whole spacecraft because we want to get as much as we can. And so it is a big push on our side to try to reduce the energy consumption. So we're talking down to like 100 watts or something like that at a time. So it could be that we store up the power when we're facing the sun and take measurements later, but it sort of depends upon exactly what we want to sense. So we will be using some form of batteries in the missions.
Yes, because that could be my next question. What about in the day when there's no sun?
No sun in space?
Yeah.
Well, luckily we're orbiting at about a 90
Rotated.
minutes sort of period.
Okay.
Yeah.
Thank you.
That's one thing we can rely on, yeah.
Thank you very much. More question? Just one more question, if there is. If not, once again, let us put our hand together. Thank you very much, Dr. Mark. We hope next time to see you live in Angola. Have you been to Luanda?
No, not yet. No, I'm waiting for the invitation.
Okay, this is the correct invitation.
Okay,
Next
great.
year, by this time, we believe you're going to be here.
Sounds good.
Okay, thank you. Bye-bye.
Bye-bye.
Reggie, you're going to help me to introduce straight away the next speaker. I just said is CV ready, Professor Dominic. If we can introduce him. Let me ask you guys are you enjoying it? And also, there is someone who is not understanding English. No? Às vezes estás a ver pouco de fumo. I can feel the lady near to Professor Gaspar like she's not understanding. It's not true. It's true. Acho que é o Prof. Gaspar que tem problema. Okay, technician, let us give us a sign if everything is ready there. We are nearly done. And we're going to eat again. I promise you, you're going to eat again when you reach home just to sleep. This is good for us who we don't have a wife in Angola. And you're not going to spend even money to the restaurant. And I hope also you are enjoying the moderation. Or not? The moderation is going well. I'm doing a great job. Okay, Mr. Dominic, we are here waiting for you straight away from Angola, Luanda. We are in Ispetek. It is a pleasure to listen on your speech. The time is yours.
Can you hear me and see the slides?
Yes. Yes.
Great. Well, first of all, I'd like to thank the organizers for inviting me to speak here today. My name is Dominic Hunter. I'm a postdoctoral researcher from the University of Strathclyde. And today I'm going to be talking about accurate and precise optic pump magnetometry for geophysical applications. So optic pump magnetometers are very diverse devices that can be used in a variety of applications, some of which I've shown here. My main focus in this talk is going to be on the geophysical applications. And with respect to that, we're really focused on optically pump magnetometers that can operate in unshielded environments, so at finite fields. So we really want a sensor that is compatible with being able to measure across the globe. So to give you some sort of perspective on that, the Earth's field magnitude can actually vary by about 40 microtesla across the world. So that's quite a significant range, and we want the magnetometer to be able to operate within that range. We also want to have appropriate sensitivity. So typically, the femtotesla per hertz level is considered really good, and this is actually about a billionth of the Earth's field, so it's all really high precision. And one of the things that OPMs can really excel at is in their accuracy. So they're sort of low systematics, and this is in contrast to things like fluxgate, which can drift over time. This is really important for likes of long-term monitoring, such as what you require in geophysical measurements. And you also want to have a bandwidth so that you're able to sort of collect data at a fast rate. So you can see how this would be advantageous, for example, if you were flying on a drone, you'd really want to increase your spatial resolution by capturing data very quickly. So you really want to have that high bandwidth. And you also want to have a robust sensor. You want to minimize the complexity of it. So that includes things like trying to minimize things like feedback loops are required. And one of the configurations that we're very interested in the University of Strathclyde is the free induced decay configuration, which we think really meets these criteria. So I'd like to thank Mark for his excellent description of the quantum technologies there. So I'm just going to go a bit into detail here. So if we have a system, for example, a cesium vapor cell, the atoms are starting off thermal equilibrium, so they're all equally distributed among the magnetically sensitive energy levels. If we then use intense pumping light, circularly polarized, we can basically send all of those atoms into the one state. So this is basically us generating a really high degree of coherence in our system. So we're preparing the spins for the measurement, essentially. So classically, this looks like the sort of macroscopic spin vector is aligned along the beam propagation axis. And then if we have some external magnetic fields, what happens is basically atoms start to precess around that field. So that spin vector is rotating around that external magnetic field. And what you can do is you can basically monitor the transmitted properties of the light passing through those atoms. And if you monitor that, you can actually see, you get a signal that looks something like this, where we have an optical pumping stage where we're preparing the spins, and then we have a readout stage, which is basically a damped oscillation where the frequency of that oscillation is linearly proportional to the magnetic field of interest. So this data I'm showing here is real experimental data, which we've taken at around 50 microtesla, which is good emulated conditions for the Earth field. So this is a probe scheme where we have basically two laser beams. One is used to optically pump the atoms, and that is intensity modulated. So the light is completely extinguished during readout. And then we also have a continuous wave probe, which is continuously monitoring. And we basically detect the optical rotation and the polarization of that probe light as it passes through the sample. And we detect that in a balanced detector, as you can see there. And our signal that we get looks something like this. So you can see we get a sequence of these damped oscillations, and then by extracting the frequency from these oscillations, we can build up a magnetic field time series, basically to detect the magnetic signals of interest. But one of the issues that we have, if we simply use just a single optical pulse to prepare the spins, to optically pump the atoms, is that the external magnetic field of interest actually causes those spins to be deflected away from the optical pumping axis. And this degrades the performance of the device. And it's basically just because of this, again, this Larmor precession, which is causing this torque. So there has been ways of remedying this that have been performed in the past. So one example is to resonantly drive the system at the Larmor frequency, so at the frequency of the atoms. This is known as synchronous modulation. Another way is to actually just null the magnetic field during the optical pumping period, using, for example, a set of coils. But what you'll notice with both of these techniques is that they both require prerequisite knowledge of the magnetic field of interest. So a technique that we've come up with to try and circumvent this requirement is to basically use a very strong magnetic field at the millitesla level, which is aligned along the optical pumping axis. So for instance, we're just pinning the atoms along that axis during optical pumping, which allows us to really improve the sensitivity of the device and really expand the dynamic range of the device. So open up the sort of static fields that we can work in, which is really useful for unshielded magnetometry. So If you want to know more information about this technique, then please see the reference website listed below. So in order to actually produce this strong field, we've developed a very simple set of printed circuit board coils, which have a square spiral pattern and mimic the geometry of our cesium mem cells, which stores the atoms, which are the magnetically sensitive medium. And you can see that they're very compact. When you look with respect to the ruler, the whole thing is a centimeter. And we drive these coils with a circuit which allows for very rapid demagnetization. And this is very important because we don't want any of that magnetic field that we're producing to leak into our measurement and cause additional systematics. So to give you an idea, the systematic we expect from this technique is around about 200 femtotesla. And this just comes from the leakage current in the MOSFET we're using in the driving circuitry. And we can attenuate that field from 90% to 10% around about 200 nanoseconds. So it's very fast, and we can be sure that we're not inducing any fields during detection. And what this allows us to do is it allows us to operate in very high bias field conditions. So I've listed 50 microtesla. That's a good baseline for what we'd expect the air field to be. And you can see from the yellow trace where we have this magnetic pulse hasn't been applied, we have a very small signal amplitude in comparison to when we do apply this magnetic field pulse, which is shown in blue. So you can see that this technique really improves the performance of the device. And one of the additional benefits of using this technique is the fact that since we're putting quite a lot of current through these coils, they dissipate heat, and we can actually use that as a secondary benefit to control the vapor density in the vapor cell, which helps us again optimize that sensitivity. And because the current isn't applied during detection, we're not sensitive to any magnetic noise that is typically associated with electrical diffuse attributes. And this is proven by the fact that we're actually able to reach the Kramer rail lower bound. So this is something that it's basically a metric which says if you have a particular signal with a particular amplitude and decay rate, there's a sort of maximum precision which you can actually get from that signal. And we reach that based on the noise floor that we actually see in our magnetometer. So this proves that we don't see any magnetic noise produced by either electrical heating or other magnetic noise sources. I'd like to just talk about a project that we're involved in collaboration with British Geological Survey and RALSpace, including Mark, who spoke previously. So I've shown just an example of some solar weather infrastructure that can be affected by solar weather. And what the project we really want to do is we want to be able to monitor that solar weather in a good way that we can basically be proactive in protecting our infrastructure. And so you can see in the right-hand side here, we have a map of the UK. So the blue data points are essentially sites in which the British Geological Survey already have deployed magnetometers. These are based on flux gates and proton precession magnetometers, which discipline the flux gates to account for any drift. And then the red data points is sites that we want to actually deploy our optically pumped magnetometers that we developed at the University of Strathclyde. So you can see we have an additional 5 sites there we want to include. And the benefit of the OPM compared to these other magnetometers is the fact that we only need one of these devices because we have the precision and stability required. So we don't need another magnetometer to discipline, for example, the flux gate. And that's really one of the main advantages. The magnetometer in question looks something like what you can see in the sort of bottom middle of the slide there. So it's a very compact device with a fairly simple optical geometry. So we basically have a cesium mem cell and a VCSEL, a compact chip scale VCSEL, which is the laser source. And then we have some additional optics to condition the beam. And it's also passed through the cell in a double pass geometry and reflected back onto our detector. So you can see from the signal that we achieve, we get a very narrow line width and good sort of signal amplitudes or signal to noise, which allows us to reach sensitivities of the level of sort of sub-picotesla, which is more than adequate for these sorts of applications. But one of the downsides of these types of systems is that they are inherently scalar, so they can only measure the magnitude of the magnetic field and they don't have the directional information or the vector information. One of the challenges in this project is to try and get the vector information from these scalar measurements, which is something I'll talk about in later slides. So this is just a magnetometer that we actually deployed in Islay in Scotland. So this is actually an excerpt from the local newspaper, a picture from the local newspaper. So basically the magnetometer itself is completely remotely operated. It's powered by a battery, surprisingly in Scotland, but it still works over long time periods in a solar panel, using a solar panel, sorry. And we're actually able to compare the data that we collected from Islay with other devices as well, which were managed in sites by the British Geological Survey. So you can see we've got three devices based on, three devices based on BGS sites, and then we also have three devices which are optically pumped magnetometers. You can see from the sort of top plot there that we have a particularly strong sort of magnetic storm which has occurred during that period, and all the magnetometer signatures seem to match up fairly well, adjusting for their geographical locations. And I've also shown a sort of baseline example of what a normal sort of magnetic period would look like in the bottom plot there as well. So this shows that we're able to basically measure these magnetic signatures in a similar way to the flux gates, but with one device. As I mentioned before, one of the problems with some OPMs is that they are scalar sensors. So how do we get the vector information from them? So I'll just take you through some very simple maths. So we consider the case where we have two fields along the y and x direction, and then we also have a modulation along the x direction, and that's basically the direction we want to get our vector information from. If we expand that out, you can see that we basically end up with three terms: a static term, a term which is at the modulation frequency, and a term which is at the second harmonic of the modulation frequency. And what you'll notice is that the second harmonic is only dependent on the amplitude of that modulation. It's not dependent on the static component. So what that allows us to do is by demodulating at the second harmonic, we can then basically calibrate our first order component and it basically just get out that sort of bx0 value, which is the vector component of interest. So this is basically a self-calibrated way, basically the atom's telling us what the vector field is. So we're not relying on prior calibration, for example, of the coils which are used for the modulation, which is really useful. And just to show an example of how this works, it's a simulation that we've got where we have a vector component which is either plus or minus 200 nanotesla or at 0 nanotesla. So you can see we get this sort of high phase change as we pass through 0. And then at 0 nanotesla, the first order harmonic basically is completely suppressed, and we're just basically going to twice the frequency. And if we demodulate and we sort of vary that magnetic field along the x-axis, we can get this linear dependence. And the gradient here is 1, as we would expect, based on what the input of our vector component was. So in terms of so as I mentioned before, we can basically get this sort of signal train where we are able to build up a magnetic field time series. So if we then have two modulations along both the y and x direction, these are the two directions we're trying to get our vector information from, we end up with a magnetic field time series looks maybe something like this, depending on the modulations that are applied. So you can see here, if we look in the Fourier domain, we have two sort of spikes at 91 and 111 hertz. And these are basically the modulations that are applied, but you can also see that they have the second harmonics as well. And these are used essentially to calibrate our vector measurement, as I mentioned before. And you can see that our baseline sensitivity remains basically unchanged. And we don't have to apply a third modulational axis, because we have the scalar measurement. Use that and use simple Pythagoras in order to get through two components. And this is just an example of us to track slow mod at both vector axes simultaneously. So you can see we've applied a 1 hertz modulation along the x and y axis, and we're able to easily resolve those two signals. However, one of the things that we were worried about is the fact that our scalar signal will be contaminated by these modulations that we're using to extract the vector signal. So we want to come up with a way of trying to recover the scalar sensitivity. And to do that, we can simply just subtract them out. So compute what the active phase of these modulations are through physical demodulation, then we just subtract the signals out. You can see based on the time series here, in the cases where we don't subtract and do subtract, we get a sort of suppression of those modulations. And that's more clearly seen in the frequency domain, where the blue spikes are completely suppressed and we basically recover our sensitivity, our scalar sensitivity. So one of the problems that we came across when we were performing these vectorization measurements is the fact that the orthogonality between our coils that are producing the modulations along the X and Y direction in this case is very important. So we wanted to come up with a strategy of trying to identify that orthogonality condition. So to do that, we came up with a system. So this is basically a picture here of what we put inside our new metal shield. Essentially is our magnetometer. So we have our MEM cell, which is inside this structure here. And we'll be able to rotate a set of coils such that we can change the orthogonality condition with respect to another set of coils. So to do this, we basically came up with this nice sort of 3D printed structure, which allows us to rotate a set of biplanar disc coils. We have two sets of these coils. One set is kept static, and then the other is rotated with respect to that static coil. And that's basically so we can change the orthogonality condition between those two coils. These coils were designed using software known as B-field tools. And what's really interesting about this software is it allows you to design biplanar coils. So even though they are sort of on the YZ plane, they're actually able to produce a field which is along that plane. And you can actually produce magnetic fields in all three directions with just biplanar coils, which is really useful for reducing the footprint of the sensor because you don't need to make coils in all axes. And this is also really good for homogeneity and things like setting your orthogonality condition, which is really useful. So the procedure we actually use for testing this orthogonality condition is actually quite simple. So we simply perform a sweep across a sort of vector axis of interest, and then we vary the bias field along the orthogonal coil. And what you notice is that we have some orthogonality present, then the center point of basically the straight line that we get through our demodulation procedure will change because of that orthogonality condition. And it's essentially because some of that bias field is leaking into the other axis. So what you get is basically a straight line dependence of the bias field as a function of that center current. And if we change that condition such that it's in the opposite direction, then we can basically reverse that gradient. And if we get the perfect orthogonality, we get the sort of exactly the flat dependence that we really want. So this is a really nice way of basically determining whether the coils we have are orthogonal. And the neat thing about biplanar coils is that because they're based on printed circuit boards, they can be very reproducible as opposed to the likes of hand-wound coils, which will be variable from piece to piece. So just to summarize, I've shown you an example of some space weather, which we've monitored with some of our ground-based OPMs. I've also shown a calibration-free method for vectorization, which allows us to get the vector information from a scalar update pump magnetometer. And I've also shown how to test coil orthogonality, and also some examples of biplanar coils we've used for vectorization. And in the future, we would really like to sort of further prepare for deployment of these sensors in the UK network as part of the funded program with BGS and RALSpace. And also, we would like to perform some more long-term monitoring in unshielded environments. So we actually have some a measurement coming up next week where we're actually going to go to one of the BGS observatories in Estelmere to perform some of these measurements. So hopefully we'll get some nice results from them. And I'd just like to take a moment to thank everyone at the University of Strathclyde. I'm very privileged to work in a great team. And also I'd like to thank all of our collaborators, in particular from RALSpace and BGS as part of the Space Weather Project. So thank you, and I'll be glad to answer any questions.
Thank you very much, Dr. Dominic. I hope that you are speaking from Barcelona or from UK?
From the UK.
Okay, that's great. Please, anyone have a question? Okay, If no question, we are happy. And I hope that all of us will learn new techniques, new skill that's going to help us for further research and also our day-to-day work. Like myself, my background is in medicine, but I'm trying to get the interesting of joining the engineering field through the speeches. Once again, let's put our hands together to appreciate the work that Dr. Dominic presented. Thank you very much.
you.
I hope to
Thank
see you soon in UK.
Great, thank you.
Okay, bye-bye. Okay, the last speaker. Our last speaker, he just arrived today from UK, and it will be great to read a little bit about his background. Can you give me 1 minute? Não soube mais, pode ficar ali, please. It's not easy someone to travel, to reach the same day and to present. This is proving is really academia. I'd like to introduce you engineering Denilson Domingos Nicolau. He holds a degree in electrical and electronic engineering, and he has spent the past 5 years immersed in diverse fields, including the integration of classical engineering in quantum system, power, electronic, RF equipment, and consumer-based product design for the broadband industry. It is a great opportunity for us to receive an Angolan who lives in the UK doing a science over there. Let us appreciate when he's coming to stage by clapping our hands. It's good if we can give the microphone, the wireless, to make him more free, please.
Eu vou começar a falar em português primeiro. Gostaria de agradecer a todo mundo aqui. Gostaria de agradecer ao Dr. Marcílio por ter me convidado e que foi uma coincidência. Eu gostaria de organizar um evento do gênero, então informei a universidade em que eu estou afiliado no momento e, por coincidência, um dos consórcios em que nós estamos envolvidos também tem a participação do SPTEC, diretamente com o Dr. Marcílio. Então, entrei em contato com o Dr. Marcílio, que era para poder saber se podíamos organizar algo do gênero. E, por coincidência, já havia um evento como este aqui acontecer. Então, foi uma mais-valia estar aqui, e agradeço a oportunidade. Now I can switch to English because some of my colleagues right now, they are watching my presentation. So they are in our kitchen, in our accelerometer lab in Sussex, and they are basically watching this live stream. So today, I would like to talk about the application of quantum sensing in solving problems like more plausible problems like tackling hunger globally. So what I want to basically highlight today is how we can actually use these cutting-edge technologies to help solving problems that it's been affecting us for for years, and how the academia can be involved, not just the political parties, but also the academia can do something to change it, even if it's minimal. So it's something plausible that we can implement. So as has been said, I'm an electronic engineer. I was one of the privileged students that got a scholarship from ISPTEC through Sonangol, and I graduate in electronics. And for the past 5 years, I've been working in the UK in a variety of technologies, and it ranges from application of radio frequency equipment for broadband, could be for applications in the distribution of telecommunication signals, TV, and internet. So that I spent my first 2 years as a junior engineer, and I basically, during that time, I was trained, and I also got involved into designing some of the equipment that is now being used in the UK as well. So I had a little bit of footprint in industry. And after that, I had a little bit of footprint as well in working with embedded systems, mostly with C programming. And lately, I've been working with, so I've already had this interest to go back to university. So when I graduate, my intention was to carry on with my studies. But at the time, the program had finished already, so I didn't have the opportunity to do masters or to do a PhD. So I tried to integrate in the industry to get some experience, but now I have the opportunity to work in an environment like this. So this is a picture of my group. So my group is composed of like a variety of people that hold different disciplines. So we work with the physicists, we work with mathematicians, and we also have a few PhD students that they are part of our group. And we are located in south of England. It's more precisely where that dot is in Brighton. So is where the university is based. And our research focus is quite broad, actually. So we are involved with quite a lot of cutting-edge technologies in the quantum realm. So our main focus is on the fabrication and also the 3D printing, atom trapping, and also the surface microscopy with cold atoms, quantum gases on atom chips. And the ones that are highlighted in red are basically where I have my footprint, which is the development of optical pump magnetometer and its applications in biomedical imaging and in applications also to scan lithium-ion batteries. So these are our main research footprint, and okay, so what I just presented earlier was just a background of where I'm coming from, but the idea is how exactly we can use these technologies. So what I want to give firstly is to provide a little bit of a background of why this problem is important. So we need to know why this problem is important and why we need to solve this problem. So firstly, I want to give a little bit of background of what is happening around the world with hunger. So there's quite a lot of people experience hunger. More than 820 million people right now are experiencing hunger. And the main root cause of these problems are violence and poverty, and also climate change and degradation of our sources, degradation of our soil. Sorry, the environmental degradation. But there's something that the academia can do. So we can also give a little bit of our footprint in helping solving this kind of problem. And at the same time, there's quite a lot of discrepancy where these numbers of people where they experience these kind of issues. And it seems like sub-Saharan Africa and South America and Southern Asia are the most affected places. And, but also we have the context of Angola. In Angola, for the past 5 or 6 years, we've been experiencing drought in the south of Angola, and it has been like a very difficult moment that the government in Angola has been trying to put effort to solve that kind of problem. And as an engineer, we look at these problems and we want to bring solutions. So, but also I want to give a little bit of, to highlight the SDG goal, which is Sustainable Development Goal, which is a set of sustainable goals that United Nations has put forward to basically tackle the most predominant problems that humanity has been experiencing throughout the years. And one of them is zero hunger. So our government has some alignment about it and is aligned to these sustainable goals. And one of the positive traits that we have experienced was between 2004 and 2006 and 2017, we actually managed to reduce this number of people who were experiencing hunger from 52% to about 90%. But if you see the graph that I put there, the graph has grown quite rapidly, but it has grown quite rapidly during 2019. From 2019 to 2021, the graph has grown rapidly. But we know why that thing has happened. So it's COVID happened, and we experienced that. So this is a little bit of background just to make sure that everyone understands why this is so important to solve. And the second background is how we can bring technologies to help tackle this kind of problem. Also to mitigate the effect of people who are experiencing hunger around the world, or regionally as well. So I have some points in there. So the first point is about the traditional methods that we are using. Some of the traditional methods that we are using, they still, they have some limitations. So classical devices that are utilized in agriculture, some of them they experience some sort of limitation in terms of drift, in terms of dynamic range. When you measure something, it doesn't provide enough dynamic range to measure a particular property that you want to measure precisely, so that you can have a little bit of a much clearer indication of what you want to do with that kind of measurement. And also, there's the introduction of technology solutions are quite crucial to improve the efficiency and also to address food insecurity around the world. So definitely technology can play a key role in solving this kind of problem. But also there is this emerging technology, beautiful quantum sensing, which is a very promising technology that has been around for years, but it's just now that there's quite a lot of interest in bringing this technology to commercial, to the public domain. So, and how we can use these technologies to have some sort of a footprint, or to optimize the sensors that we already implemented in in applications such as agriculture. So I have a picture there on the top. So that is actually one of the things that we probably should be, is going to be happening in the next years. So it's called precision agriculture. So precision agriculture is basically the use of technology, multiple sensors around the agriculture system. And then you can interface these sensors all together, and then you can interface them such that you can have a correlation of all the measurements that you are taking, and you can make some decision about those measurements. So instead of just looking at the temperature or at the humidity of the soil, you can basically interconnect all of these devices, and then you can make some sort of a correlation between the measurements that you take. So this is actually a very good picture for this kind of application. And also, there's some basics of quantum sensing. I think most of my colleagues and some of the speakers here, they've already given a little bit of an introduction, but I just want to be brief about it. So what is actually quantum sensing? So quantum sensing is basically the use of quantum mechanic theory to measure a particular physical quantity. The same way the physical or classical sensors are used. Classical sensors are based on classical physics, Newtonian, and such. So the same sensors, they can capture physical quantities such as temperature, acceleration, and velocity, and humidity as well. The same way, or magnetic field, the same way quantum sensor can do, but quantum sensor has a much better advantage over classicals. So principle of operations are some of my colleagues or the speakers here have already mentioned. So is around the manipulation of measurement of quantum states, utilization of individual atoms and ions, and superconducting circuits, and the exploration of quantum effects and such. So these are basically the principle of operation that govern the basics of quantum sensing. And the next one is, I want to give a little bit of background as well on the same thing about quantum sensing. The advantage that they can bring. So there's quite a lot of advantage that these sensors can provide. So they have increased sensitivity. So in case where you want to measure a very small particular physical quantity, there is quite a lot of sensitivity if you can use this type of measurement. Also, it can enhance precision and improve resolution as well. So types of quantum sensors. So we are just talking about here, but there are many types of quantum sensors. And I think one of the most, goes under the radar is the atomic clock. So most of people don't know, but atomic clock is being used for GPS. So it can provide a very precise clocking for positioning around the world. So I think everyone has a smartphone. So if you have a GPS, it's basically based on that. So it's a quantum sensor. Also, we have atomic magnetometers. So atomic magnetometers are type of sensors that can be used to measure magnetic field. So this is what I'm about. So I'm about magnetic sensors. I'm about magnetometers. And then we have quantum accelerometers, and also we have atom interferometry. So in there, on your right, I have a picture. It's the basic principle of optical pump magnetometer. Optical pump magnetometer, it aligns inside of atomic magnetometers. So how it works, how we can measure magnetic field with optical pump magnetometers. So we have a photo detector on your left, on top. So it's the top picture. And then inside there, which is the blue cube, is a glass cell. So this glass cell, it will have some atomic gas, and it's an alkaline gas. And the one that we use is a rubidium. And then this rubidium, so before we pump a light, the rubidiums, they are just scattering around. But as soon as we set the laser, so we have a laser, and then we polarize the atoms of rubidium. So the atoms of rubidium, they align with the photons of the laser. And then if you place external magnetic field, the alignment of the atoms inside of the cell, it can change, and then they become perpendicular with the external magnetic field. So this magnetic field, this variation in alignment, we can measure the variation of alignment by using a photodetector. So a photodetector can detect the light that this alignment can produce, and then from that we can basically try to measure that quantity and detect the field. So the next one is just want to talk about more how sensitive the sensitivity of the quantum of optical pump magnetometer. So one of the advantages is quite sensitive, and it has a sensitivity of about can reach sensitivity of femtotesla. So femtotesla is one of the quantities that describe magnetic field. And so in that picture there, so we have one of the arrays that we are working on. So this is one of our sensor head on the bottom there. So this is one of the sensors that we are developing at Sussex. And then also, this is one of the critical points for this type of measurement. So these type of measurements, they need some sort of a shielding, because because of the sensitivity of the sensor, it needs to be shielded so that no external field can interfere with the measurement. So we have these big shields in our labs, and then we can use them to do our measurements. So we can put any device on the test in there, and then we place our sensors, and then from there we can do our measurements. So we can eliminate all the external fields. So this is the modular. So this is a picture again of our sensor that we are developing. So we are trying to develop a modular OPM. So it's like to try to make it as an array, because if you use it as an array, there's quite a lot of application to use as an array, and I'll explain that later. And also, so this is one of the case studies. So Dr. Teresa has mentioned about how we can use quantum sensing to basically to do some more tangible measurements. And then in here, I have a case that I want to make about the use of quantum sensing to detect nutrients in the soil for agriculture purposes, to be fair. So, so how we do it? So we know that magnetic sensors, they are sensitive to magnetic field. So if we want to measure the nutrients, so before, why we need to do that? So why we want to quantify the nutrients in the soil? So the reason why we want to do that is because some of the practice that has been happening in agriculture involve the use of quite a lot of fertilizers. And these fertilizers, sometimes they can be overwhelmed to the health of the crops. And sometimes these fertilizers cannot be absorbed by the crops, and they end up going through to the river, and then they end up joining the water. And then sometimes these waters are the ones that get back to our houses. And so if we can quantify the level of nutrients inside of a sample that is a sample that is fertilized for the use in agriculture, we can quantify the level of fertilizants that we need, and we can, in some cases where we don't need that much fertilizants, we can reduce it. So this is a good case that I want to make. And the way we do it is by using nanoparticles. So we use nanoparticles like oxide ferrite, and so we use nanoparticles such as oxide ferrites, and then these oxide they can have different magnetic properties. So they can be diamagnetic, paramagnetic, ferromagnetic, and such. So depending on the interaction of these oxide with the soil nutrients, we can detect what kind of nutrients are in place in the soil. And then we use that scheme, which is a hysteresis scheme that detect the momentum of these particles. And then depending on that, we can detect what kind of particles are in the soil, so we can remove it. So those particles that we infer, those nanoparticles, they can be removed because they are magnetic particles, so we can take them apart. Then we can differentiate them with other nutrients that are in the soil. So there's quite a lot of advantage by doing that. So this superior sensitivity, and also can be used to do real-time monitoring. So if we can create the scheme to implement that technology, so it's quite remarkable. So this is a potential. So this is one of the potentials that we can use. So the next one is also a case study that I want to make about water management. So the case that I want to make is the same as that I mentioned earlier about fertilizants. So these fertilizants, sometimes they can go back to our water treatment. And sometimes they can pass undetected, and then they are quite poisoned, and then they are quite pollutant. So some of the systems that we have in place, they don't provide enough insurance or assurance to remove those kind of pollutants. So we have there is a measurement of that has been done in water. So in that measurement there, what we have is we have a tube that we insert a fluid, in this case water, and then we magnetize before it reaches to the magnetic sensor. We magnetize to create a momentum of the particles inside of the fluid, and then after some times we measure that momentum. And then if there is any sort of fertilizer or any pollutant that are magnetic sensitive, we can detect it with our magnetic sensor. So there I have some picture of the graph of the experiment. So in the top there I have the experiment that was done, but is in a time domain. So in time domain, it doesn't provide enough. Indications of what is going on, and then we switch that to frequency domain, which is the one on the bottom, and then we can see the difference in terms of amplitude with the black one, which is the noise, and the top one is basically the magnetic metals that are in this liquid. So then what we do, we use some statistical model to quantify the level of these quantities, and then we can see the magnetic amplitude when there is those components inside of the water, and then we compare those ones with pristine water, so it's like proper clean water. Then we can identify the type of materials that are inside of the water. So this is also another case that I want to make about how we can use this technology. And the next one is this is an indirect type of. Okay, yeah, I'll try to rush up. So this is an indirect way that we can use it. So it's about power, but also is related to food insecurity. So this is some numbers that are there is how electricity has been affecting agriculture, especially in South Africa. So it has been so from March last year, it has estimated that they've lost about 7.6 billion of rands. So due to electricity shortage, and then so one of the most affected ones are irrigation. So when there's blackouts, they usually create quite a lot of frustration in terms of productivity in agriculture. So, and as a result, there's a rise in food insecurity, and with an OCP reaching about 7.1. So this is one of the cases I want to make. So seeing that case, I want to demonstrate one of the applications that we've been doing at Sussex, which is use of our OPMs to map lithium-ion batteries. So lithium-ion batteries are basically a go-to technology when it comes to mobile power, especially for electric vehicles. So there's quite a lot of rise of electrical vehicles lately, and these electrical vehicles, they use quite a lot of lithium-ion batteries. The reason why we use lithium-ion batteries is just because of the energy density that this type of technology can produce in terms of energy density per kilogram. So to move a very large body, it needs quite a lot of energy. So, but the application of that is for when it is integrated in electrical vehicles. After some times, these batteries, they degrade. So with the help of optic pump magnetometer, we can provide a diagnostic tool to basically to look the current density inside of these used batteries. We can look and detect some defects, and then for applications such as electrical vehicles, they need quite a lot of energy density by kilogram. There are other applications such as irrigation that might not be in the same kind of that might not require that kind of parameter. So we can actually reuse these batteries to implement in places like remote, to provide some sort of remote power for water irrigations in pumps. So because it's well understood that there's quite a lot of micro agriculture, and some of the places they don't have access to water. And by providing a technology that help recycle these batteries that were used once for electrical vehicles, they can also be used for all sort of less power-hungry application. So at Sussex, we are developing this technique which is a maintenance tool for electrical, is a maintenance tool for lithium-ion batteries. So in here we have a picture of, the battery. This is the picture beneath there is the inside structure of the batteries, which we have electrodes. So the key parameters that we are basically trying to look at is the state of charge, state of health, and state of capacity loss. So I'll try to be brief. So these three parameters are being used in our mobile phones. So it can detect how well our battery can sustain power. But this is a non-invasive type of measurement. So what we do, we place our sensors in that configuration. So we have three sensors that they are configured in a gradiometer. So we configure these sensors in a gradiometer because it can provide a much better signal-to-noise ratio performance, and also can eliminate the effect of the far field. And then it can give us a much better resolution when we look at near field, which is the field of our interest. So in there, we have a discharge pulse. So we discharge the batteries, and then we do an open circuit type of measurement where we want to detect the parasitics of the electrical chemistry of the battery. So these electrical chemistry parameters can provide an image of the current density inside of the battery. And then by looking at that, what we can do is we can try to predict if a battery can be defective, or if one of these electrical chemistry parameters can be mitigated by some other factor. So these are the results that we have. So on the top left, we have the magnetic field. So basically what we've seen there, we have 6 sensors that they are connected in a gradiometer configuration. So in a gradiometer configurations, what we want to do is to create an image of the current inside of the battery. So if we can create an image of the current inside of the battery, we can understand what is inside of the battery by recreating the current by using the magnetic field that we are measuring. So by doing that, what we do is we let the battery at open circuit, and then we measure the relaxation of the battery. So what we see there is the battery, after being discharged, we switch it, and then as soon as we switch it, it becomes an open circuit, and then we see that relaxation in there, and then that is when the battery is trying to get to the steady state. But before it gets to the steady state, we see that it has this kind of decay. And then by using a gradiometer, we can look at basically how this decay is affecting the battery. So this can give some sort of indication of what we can give some sort of indication of the battery. And then we compare those results with the state of charge. We compare that with the state of charge. But state of charge is an average type of parameter. So it's not like something that is very precise, because state of charge is basically the rate of change of the capacity of the charge of the battery over time. But if we can basically have a way that we can measure the battery current when it's discharged, we can actually see smaller and more defect, because the currents and the parasitics are more sensitive when the batteries and the current of the batteries are very small. So this is one of the type of measurement that we are doing there. So I'm just about to finish. So we have challenges and considerations. So the current landscape challenge is the technology that we are developing is quite premature. So it's quite premature. It needs quite a lot of time to research. As any other technology, it basically it needs more collaboration with other entities, and there are also some cost consideration as well. So at the moment we are on the concept, because premature, we are in the concept of getting these technologies into the market, but we still need more research around it. And then also integration. So there are some, it's not quite easy to integrate this system with the current sensors, or with the current system that we have in place. And so visions for the future. Visions for the future, for me, this is a personal opinion. I think what we should do is try to foster more collaboration among peers, and then try to bring people that are in other disciplines as well, to bring them together, and then we can discuss how we can try to implement some of these applications into other fields as well. So that can give a little bit of a food of thought to both parties. And also, this one thing that I want to show is basically the impact of these technologies comparing to other technologies such as quantum computing. So this is not the topic, which is quantum is about quantum technology, but also quantum computing is part of quantum technologies. So in that graph there, it has the sustainable goals, and then the impact of the sustainable goals comparing to the technologies that we are talking about. So we see that for zero hunger, in terms of quantum technology, simulation and quantum machine learning has a much better impact compared to quantum sensing. Because what I was talking about earlier, about precise agriculture. So precise agriculture will need quite a lot of analysis, and then it can provide a much better overview of the type of, so it can provide simulations, can predict type of soil, can predict type of nutrients that we can implement, can provide much more impact comparing to quantum sensing. But we also can leverage the impact that the quantum sensing can provide for this type of applications. And for summary, I just want to say that the summary for these is traditional methods, they face challenge, of course. But the technology that we are developing is still premature, but we also can see ways that we can work together with current technologies and these emerging technologies. And quantum sensing is basically offers quite a lot of advantage, such as precise measurement and increase in sensitivity. And lastly is the summary that I want to also highlight is there need to be a continuation of investment. Because one example I want to give is about the semiconductor. In the 50s, when the semiconductor was a niche technology, it was a different sector, such as telecommunication, that put a lot of investment. And then now, in all the fields in our society, is full of semiconductors. And then this can happen as well for quantum sensing. So I want to say thank you again, and I want to give big thanks to Dr. Marsilio. I want to give thanks to my colleagues back in Sussex. They are probably watching now, and thank you, everyone.
Thank you very much, engineering. Please, can you take a seat?
Sorry, it was quite long, but I had to cover some of this stuff. Sorry about that.
Yes, I did not cut you off because you travel abroad from
no.
UK, you spend more than 12 hours.
Yes.
It's not easy to travel for more than 12 hours just to come to present for us. Professor Artur, this is the reason that we did not cut him off. Can you clap again?
Thank you. Thank you very much.
It was long,
Yeah,
but
it was very
good
long.
and great
Yeah.
information. I believe next time, when you're going to travel for 4 hours, it will make it short.
All right, yes.
Okay, let us collect even one or two questions quickly before inviting the host of the workshop. Yes? Please help us because the food is ready there. We don't want to eat it cold. If you make long question, the food is going to get cold.
Okay, my name is Miguel Clement from INSTA-QT. So it's such an interesting subject, I can call that like that, good technology. But my question is how the less developing country can afford this technology?
I was expecting that question, to be fair. I was really expecting. And
Angola.
Yes. I've been having this conversation with my colleagues, and they highlight that as well. We had a little bit of conversation about that. So I think what should be happening is, as an engineer myself, I think what should be happening is, throughout the development of these technologies, we need to change the system where how we produce this type of technologies. So we need to think more broadly in terms of implementation and reach. So as an engineer, what I want to do is not just to produce something that can help people, but also I need to look into other parameters such as component price, how we can make this type of equipment available to people with low income. So, and also we need to have some So we need to have some kind of incentives as well from third parties, such as the government and such, because I think what should be happening is these technologies are out there, but we also need to think about how these technologies can be accessible to other people. So how it get cheaper. So one example I want to give is go back again to the semiconductor. In the past, we were using transistors in a valve, which was really expensive. And the first transistors, when it came on, it was expensive. But because of the big investment that was put in place, those kind of technologies, they start becoming more accessible. Right now, a piece of semiconductor can be around less than $1. So, but if you are designing a system that requires quite a lot of equipment, so there's quite a lot of you need to be a little bit mindful how you are placing those kind of components, because you need to think about your reach, how you want to make this technology be accessible to other people. So there are the government intervention, there are third-party investments. So all of these three, all of these parameters that I just mentioned can help boost these reach to places where are less fortunate, or they can have access economically to this type of technology. So right now, it's pretty expensive. So one of these components that I've just mentioned there is around, can be around 300 or 3,000 pounds. Sorry, 30,000 pounds. So it's quite expensive. But
okay, I think we get the answer. Thank you very much. We can applaud Thank you.
Thank you.
Prof. Altori, do you have a question also? Oh, please. Come sit down. Okay, we can collect 2 more questions. Make it brief.
Can I talk first?
Prof, please, you need to use microphone, otherwise Professor Thoms is not going to understand.
I have a question too.
Yes, let's start with you, please.
Yes, my name is Francisco. I have a question. What is the difference between quantum sensing and the geophysical method? And what does quantum sensing measure? Because I heard a lot about magnetometry.
Oh, yes, okay. Quantum sensing is a very broad sensing realm. So, as I said earlier, the quantum sensing is the use of quantum mechanics theory to measure physical sensors. So the physical sensors, they are not just limited to magnetic field, but they also can be used to measure acceleration, gravity, as gravitometers, and all sort of physical quantities. The same way that we use classical sensors to measure temperature or humidity, there are also ways that we can use quantum sensing. So the only difference is the laws of physics in this type of sensors are just different, a little bit different. But so the classical sensors, they are governed by Newtonian law or Newtonian physics, and the quantum sensors are governed by quantum mechanics. So it's just this difference.
Thank you very much. We can see that you are a good disciple of Professor Marcelo. You are doing well. Okay, the last question.
Yes, please. José Augusto, ISPTEC. It's always good when good sons return home.
Yes.
And for that, I congratulate you.
Thank you.
Yes. I was amazed with all the presentations.
Thank you.
Specific your presentation, because it's specific to bringing new technology to our country.
Yes.
And this is perfect. So now my question is not very technical on whatever numbers you presented, but it's taking into account our reality.
Yes.
So based on the Angolan context and in your perspective, what do you think is the most accurate and realistic chronogram that we can put this technology in place?
I'll try to give the context of Angola by trying to look into a context of the world, and then I can narrow down a little bit. So
Just 2 minutes.
Yes. So quantum sensing are very close to reach the market, but there's quite a lot of things that need to be done. And so if I have to place a chronogram, so it's basically being said that in 5 years, we're gonna start commercializing quantum sensors. But in our context, it takes a little longer for these emerging technologies to reach low-income countries such as ours. And I think it's just a systematic thing, and I think that there should be something, or there should be some kind of incentive that need to change this kind of systems, because in a broader term, it would take 5 years to reach the market, but for our case, I think it will take a little longer. Yeah.
Thank you.
Okay, once again, let's put our hand together.
Thank you very much.
Thank you very much. Almost done. Long day, but good day. Please help me to welcome the host of this event. But before that, let me tell you something. I wrote an article, and I said that without of technology, there is no development to the country. If we want the GDP of our country to increase, if we want to have more professionals, even our country to be accepted academically in international level, we need to work on the technology. And this kind of activity is opening our mind, calling our attention, also is increasing our vision. What is the vision? Vision is the capacity to see what people they cannot see. I would like, and I will ask you to put your hand together for the vision that Professor Marcelo he had to organize this kind of event. Let us appreciate this vision by clapping our hands. I'm inviting Professor Marcelo. I don't know if I have to read again your... Anyway, we know that Professor Marcelo, he used to be the direct manager of ISPETEC. Oh, you forgot that?
Thank you. Thank you very much, everybody. It has been a long day. I hope you guys got some information about quantum. Quantum is awesome. That's why I did my PhD in quantum physics. And I'm glad to also be part of INSTA, which is the international network of sensing and timing application from quantum technology. This INSTA is sponsored by many partners in the UK, to which I congratulate and thank a lot for what they do. So everything that you saw today, it was sponsored by the UK, you know, the INSTA partners and sponsors. So one thing that I received from Joanna, who is the now leading person for all these services about the workshops, is that to let you know that the University of Birmingham, where she is, and the partners of INSTA-QT projects are very open to collaborations and sharing experience in fields of quantum technology. So anyone who is interested in getting collaboration about the quantum technology, it is open. Also, she asked me to tell everybody that because this tech is part of the INSTA network, there will be a set of staff, academic staff, that will go to UK to visit the installations of quantum laboratories in UK, mainly University of Birmingham. So INSTA is a network of about 51 institutions. ISPTEC is one of them. There is University of Birmingham, Strathclyde, Sussex, and many other institutions. We also, Dr. Mark from RAL. When I did my PhD, actually, I had my supervisor from RAL, and I'd like to thank so much Dr. Hall and maybe send him some greetings to my supervisor, who was very excellent in what he did. Also, I would like to thank everybody who are up to this time here, mainly the inviters, the speakers, Dr. Teresa, Mark, Dominique, Alan, was Tom King,
Joanna herself. We were expecting the Secretary of State as well today, but unfortunately there was some delay because she had another urgent meeting to attend. It's a political related meeting, so she didn't come, but she sent her regards and also thanked the INSTA for the organization. Also, and not least, thank so much Dr. Zolano. Maybe you didn't, some people don't know really Dr. Zolano, but Dr. Zolano is the leading person on the space program in Angola. So all about the ANGOSAT is related to his work and his direction, what they are doing exactly at Japan. So thank you so much for coming. We would like to, in short, this workshop is designed to help connecting different areas of knowledge to also sort out some problems. And this problem is food. We don't want hunger in the world. And we believe that quantum technology can help. And that's why we have this set of workshops and allow people to know that it is possible to use new technology and reduce the impact of hunger. We also had the talk from Dr. Américo, who I thank so much as well. Although he spoke in Portuguese, but there were a lot of golden nuggets in what he was saying. He explained a lot of things about the distribution of water that we have in Angola, and that's very important for this talk, because what we have is a drought from Cunene and other provinces, and they have difficulty in getting water. The technology that Dr. Mark, Dr. Dominique, and Alan, they were speaking is actually to facilitate getting this water. So Dr. America said that they spend about 15 million kwanzas for one well, and sometimes they don't get water. So you need technology like this to survey the region and make sure that you will get water when you have to drill. And so you spend less. I heard also some question about how expensive it is and how long it will take. This is how thing works. If we have debt for construction, if we have debt to diversify agriculture, we have to have debt to make technology, because technology, the advantage of that is that if you improve in technology, you can sell it. And you can improve also the lives of your people. There is no way to do better if we don't increase our, the amount of money we put into technology. There is no way. Otherwise, we will always buy technology. So we are delaying our development by saying, okay, we spend too much there, I have to spend elsewhere. But we have to think long term. You cannot just think now. There are some investment you have to do long term, and technology is long term. And our people deserve it. So, and that's the reason why this type of program exists. It's a collaboration about many, many countries. There are people from different countries in the INSTA. So it's a program that you can imagine. We have some workshops in Thailand. We have in UK and elsewhere, Mexico. So different countries with different problems, but the same type of technology that can allow these problems to at least reduce or go away. So it's important to think long term, not just short term. Okay? Sometime in the future, maybe Earth will be in a collision with an asteroid. And I always say to my students, what do you think, who do you think will solve the problem? This is not the lawyers. They will not solve any problem related to asteroid. You have to be us engineers, scientists. We have to figure out things before they happen. So thank you to President of ISPTEC. Thank you, Dr. Cirillo and his team for allowing this to happen. And thank you all of you for being here, bearing us all this time. Thank you, Joanna and the team. They're back in UK, and we will send you the report, and
talk more about this. Thank you very much. Let's go for the coffee break. Thank you.
Okay. Before going to the coffee break, we're going to take a picture.
Yes, he said.
Even no one claps his hand for the moderator. This is not fair. Oh.
Yeah. Thank you to him. That's true. Dr. Vita.
Please let us come on front. We're going to take one picture. It is very important for Dr. Marcel, when you're going to do a report, can you add even a picture? Please, let us come. Ask Dr.